a collimator to get radiation in the direction that we need. So, but the situation is source will emit in all directions. Yesterday, when we spoke about principles of radiation protections and safety, we spoke about 3 principles: justification, ALARA or optimization, and limitations. Always, we need to do our practice in ALARA principle. And to do this, we have 3 ways to achieve ALARA principles. The first way is to decrease time of exposure. To achieve ALARA, we need to decrease time of exposure. So now we minimize the dose values. Increasing distance from the source also to decrease the dose that the person receives, and use shielding. So to achieve ALARA, we can do through decreasing time, increasing distance between us and the sources, and use shielding if it is applicable. Let's see how time will affect the dose that a person receives. Today, inshallah, it will be all calculations. There is no any theoretical part, calculations. So please be with me for calculators, because I don't have here calculators to help me for the results. To be easier for us and fast also to make a training for more and more examples. Okay, let's see how time can affect the situation. Time effects. Of course, we can say the dose that a person receives is proportional to time. If I, for example, stay 1 hour, I will get a dose, a certain dose. If 2 hours, I will get double of dose. 3 hours, 3 of the double of 1 hour. If I stay half hour, it will be half the dose that I receive. So it's proportional linear with time. Okay. Always we use the detector to get an indication about dose rate in the site. And the dose rate from the detector, as we said yesterday, it is a rate per hour. So our principal dose limit is 20 millisievert per year. 20 millisievert per year. This is called principal. This is by law, I can't exceed it. How can I reach to it? No problem. For example, assume this is the time. Assume this is the time. This is the start of year. This is the end of the year. This is the end of the year. I can take this 20 like this. Slowly, a little, fast, a little, fast. So here, how to reach to 20 is not a matter, but don't exceed this 20 millisievert. So I can reach like this. 1 jump, 2 jump, this is the dose I receive each day. So whatever the dose rate here, no problem. But don't exceed at the end of year 20 millisievert. Just you receive to 20, even after 1 month, 2 months, 3 months, stop. You reach during 1 year, okay, you reach 20. After 1 month, stop. You can't now work more. Stay until the next year and start working. So how to reach, no problem, but don't take during the year more than 20. So now, this year is working year. As we said yesterday, we work by this system. We work 8 hours per day, 5 days per week, 50 weeks per year. Then we can say we work 250 days per year, 2,000 hours per year. We can say also we work 40 hours per week. As right, okay. Now we have a system now. So now if we say what is the use rate in hour, as we see in the detector to make a comparison, we can say 20 millisievert, and the year is 2,000, as we say yesterday, 2,000 hours working. So this will give you 10 microsievert per hour. This is called not principal. This is called calculated dose rate, calculated limit dose rate, or sometimes called derived. Derived when you derive something with meaning, you reduce it. اشتقاق. Derived it as you derive, for example, the velocity is the ds over the. This is you derive the distance, velocity from distance with time. This is the derivation. So now this is derived, not principal. And there is a condition here. You can't work in any radiation field greater than 10 microsievert per hour if you work every day 8 hours per day, 5 days per week, 50 weeks per year. Each hour, each second, each day, 10 microsievert per hour. Your detector, 10 microsievert per hour, 10 microsievert per hour. So don't exceed this. To reach at the end of the year to 20 millisievert. But this is not the real situation. We work in variable, in variation. So we can, as I told you, adjust our work that we can work in 20 millisievert, 20 microsievert per hour. We can work 100 microsievert per hour. We can work in 70, 200 microsievert per hour. But you need to adjust your time. Adjust your time. To reach at the end of the year, don't exceed more than 20 millisievert. Let's take an example to explain this. Let's say a person works in radiation level or dose rate, let's say 80 microsievert per hour. Can this person work in this radiation level? I will say, if it is normal working conditions, no. Normal working condition meaning 8 hours per day, 5 days per week, 50 weeks per year, cannot at all. Why? Because this is greater than 10 microsievert per hour. For the international system of working, cannot. Because if you work in this, at the end of the year, you will get 160 millisievert, and the limit is 20 only, so cannot work normal. But can he work and I can adapt the time? Yes, he can work. How can I control his time? I will control like this. This is what? 80 microsievert per hour. What is the limit for normal? 10 microsievert per hour. How this is greater, how much it is greater than the normal? This is greater than 80 over 10. It's greater 8 times. Greater 8 times. So reduce time by 8 times. Reduce time by 8 times. I will ask, how many hours he can work per day? In this radiation level, I will say he worked 8 hours per day normally. Now, I need to reduce this by this amount, 8. Divided 8 hours normally by 8. Why 8? Because this is greater than normal by 8 times. So 8 hours per day divided 8, it will be 1 hour per day. He can work only 1 hour per day in this radiation level. So he can 5 days per week, 50 weeks per year, and each day work 1 hour only 1 hour. Okay, again, if a person work in radiation level, let's say 100 microsievert per hour, can he work normally? Of course no. Why? This is greater than 10. But can he work and adapt time? Yes, he can work. How? I adapt his time. I will say this 100 is greater than 10 always. Your regular system divided by 10. Always divided by 10. Okay, 100 is the radiation level in the field. How much is greater than this limit? Okay, divided by 10, it is 10 times. This radiation level is greater 10 times than normal. Now I ask, how many hours per week? How many hours per week? You will say, he worked, this person, he works 40 hours per week, divided by 10 times greater. So he will work only 4 hours per week. 4 hours per week. He can work 1 hour and stop in the 5th day. He can work 1 hour in 1 day and stop during the rest of the week. It is not a matter, but 4 hours per week. The person working in, let's say, 160 microsievert per hour. Sure, cannot work normally, but he can manage through time. I ask you, how many hours per day? You would say this is greater than 10, how many times? 16 times. 16 times greater than the normal. So now I will say, how many times greater? 160 divided always by 10. It is 16 times greater than the normal. Now reduce the time by the same amount. So how many hours per day? Normally we have 8 hours per day. You need now to divide it by 16. It is half hour per day. 30 minutes only. Work each day 30 minutes. And become 5 days per week, 50 week per year. Only I change this. So now, in case of radiation level is higher than the hour limit, the Reichert limit, 10 microsievert per hour, the worker can work, but with less time, not 2,000 hours per year, not 8 hours per day, not as normal system. Now we have another system. We need to make a new system like this. Half hour per day instead of 8 hours per day. For example, in exam say, there is a person who is responsible for the store of radioactive source. And inside the store, assume this is the store, this is the radioactive sources, this is the person who responsible about this. Now, assume the dose rate here inside this store is greater than 10 microsievert per hour. Greater. Dose rate is greater, dose rate is greater than 10 microsieverts per hour inside the store area. You can control his dose by make many barrier here, physical barrier, to know one can enter, make control by both cameras, by change the distance, by time. Of course, any dose like this, in area like this, confinement, this is a stored area, defined with area, defined area. So the only way to control the dose for this person is time. Time. If it's greater than 10 microsieverts per hour in room like this, will control time. Don't enter this 2000 hours per year. I will measure this dose rate. And now I will see how much is greater than 10. Assume I found 40 microsieverts per hour. I will say 40 is greater than 10 by 4 times. I will reduce the time here 4 times. Instead of enter 8 hours per day, I will say only 4 hours per day. So I control by time. I control his work by time. So in case of something like this, control this situation to not exceed the limit by time. This is the time. How can also I apply other for distance, increasing distance? Of course, if this is a source and I'm standing here, there is a dose. Let's say this is that between me and this source is S1, distance S1, 1 meter, 2 meter, 1.5 meter, whatever. And the dose here, assume, dose rate. This is dose rate. I put dot here, dose rate. Is this point is number 1, D dot 1. I know at any distance, S1, any distance, S1, like I said, the distance will be, the dose will be D1 dot. From this direction. I told you the source emit in all direction. Okay, the dose in this circumference, this one here is the same. Why? Same distance. So the dose here is the dose rate here is the same dose rate here as the same dose rate here. In any direction, no problem. So now, if the dose rate at the distance is 1, for example, I know that the dose rate at a different distance, let's say this is S1. Another distance, let's say this is S2. The dose rate here is D1 dot and D2 dot. Dose rate here, D2. Dose rate here, and I know D1, this one is greater than this dose rate. When you move away, dose rate become lower. What is the relation between S1, D1, D.1, S2, D.12? We found that dose rate is proportional to 1 over S squared, distance squared. As you see, inverse proportion. Not with distance, with the square of the distance. Not with distance, with the square of the distance. So we can write this by this way. D1 dot S1 we need to put that square. D dot 1 S1 distance 1 is not clear?
ممكن تعيد النقطة بس اللي من شوي يعني هذه. Yes, exactly.
The relation between dose rate and the distance is when you move far away, the do increase now the distance, increasing distance. This dose rate is reduced, become low. But if I increase, for example, if this is 1 meter and this is assume 4 microsieverts per hour, 1 meter and 4 microsieverts per hour. Now, if I 2 meter now, I increased by 2, double. This dose rate, this is 4, will be 4 over 2, 4 over 2 like this. Now distance increased by double, 1 meter become 2 meter. Now this will be decreased by, this is 4 over 2, no, not linear. This is will be 4 over square of the distance. So it is 2 square divided by 4. This is the meaning. Dose rate, as the distance increase, this dose rate proportional to the inverse of 1, but this is distance square. So we will write this is in this way. D, I will write this, D dot is equal, D dot is equal, another D dot is equal, another D dot is, what is this? I will put in a square, I will put a square, I will put a square, I will put a square. Going to 1, going to 1, going to 2, going to 2, going 3, going 3, going to 4, going to 4. At point 1, multiply that dose rate at point 1 by that distance at this point, but square, equal. The dose rate at another point, at the distance square. Another point, point 3, and the distance between it and the source, square. Another distance. D4, this is the dose rate. By the distance, square. Let's take an example. Assume this is the source. Now, this distance is 3 meters. Dose rate here, let's say 100 microsieverts per hour. This is the dose rate here at point 1. 100 microsieverts per hour. And this distance is 3 meters. Now, what is the dose rate here? I don't know it. At point, another point, number 2. The distance here, let's say 10 meters. So I know dose rate at a point. And what is the distance? I know the distance at another point. What is that dose rate? I can calculate it by this way. D is equal. D is 1, 1, going 2, going 2. Square, square. Dose rate. D1 dot S1 square equal. D2 dot S at this point square. Now, D1 dot, the dose rate is 100. Distance is 3, but 3 square equal, this is, I don't know, D2 at point 2, the dose rate, times what is the distance? 10 meters, but 10 meters square. So now, this is 100, and this is 100, move together. So, D dot at point 2 here is 9, what is this? Microsieverts per hour. 9 microsieverts per hour. 9 microsieverts per hour. So now, this is how to calculate dose rate at a certain point. If I know the dose rate at another point by this relation. As you see, we increased here the distance about 3 times, greater than 3 times, about 3 times. About. The dose rate here is not reduced by 3 times to be 30. No. By how many? By 3 square. So now it is 9 microsievert per hour. 3.3 square. So it is not linear, it is square. So the proportion now is dose rate proportional to the inverse of the distance square. Okay, now let's take another example. This is the source. Now, at, let's say 1 meter, the dose rate assume 4 millisievert per hour.
دكتور
4 millisievert per hour, 1 meter. Can the person work normally? I say normally. At this radiation value, normally. You will say
no.
no. It's greater than 10 microsievert per hour, so much. It's greater than 10 microsievert per hour 400 times. 100 times, okay, I will say yes, 400 times. If this is 4,7 microsievert divided 10, it is greater 400 times. So reduce that time of work 400 times. He will work only 1 minute, 30 seconds, something else each day. He cannot do this, of course. This is not way. A person work only less than even one minute every day. I can't use time here. Because if I use time to control, okay, less than 1 minute each day. With the support, 400 times greater. 8 hours per day divided 400, it's nothing. It's nothing. About 1 hour each day. So time is not practical in this situation. How can we solve this? I will say, okay, you can increase distance. I can increase distance. Now, my question is, what is the minimum? What is the minimum distance he can walk at it without exceeding the regulations, the limit of dose? Now, give me at least, this is the minimum distance. You can stay far away from the source. Don't go here. If you go here, you will increase that, you will get a dose greater than 20 millisievert per year. This is the limit. Now, what is the minimum distance? I need this. This is. I need this is minimum distance. So we can walk safely. How can we solve this? I need idea from you.
We can use the minimum dose rate allowable.
So this is 4 millisievert per hour, 1 meter. I want to know the distance, I want to know the dose rate. So this is the relation. D1, S1, D2, S2, square, dose rate. I know this. I know distance, this. But I need to calculate this S. But I don't know this dose. Can you give me value for this?
10 microsievert.
10 microsievert. 10 per hour.
To work normally here must not exceed than 10 microsievert per hour. I need minimum distance. Don't go near like this. You can walk here, for example. But this is that I can't exceed or go through this. This is the minimum. So it is 10 microsievert per hour. So this one is the limit. 10 microsievert per hour. Okay. So now, D.1 is 4 millisievert per hour, between brackets like this, to remember it only. Multiplied by distance, it is 1 squared, equal this 10 watt micro sievert per hour. This is now milli, this is micro, cannot be used. I need to make this micro or this milli. Milli and convert this to milli. Or this is micro, convert this to micro. Must be the same. So now, I need to change this to become micro. I will do this, micro. So this now, I will move this M and put M. I need to put micro now. I need to move this M and put micro. To do this, I will multiply by 10 to the power 3. And now it is microsievert. So I will write it now. So it is 4 10 to the power 3 microsievert per hour. This is 4,000 microsievert per hour. For millisievert is 4,000 microsievert per hour. I put now 4,000 microsievert per hour. Multiplied by 1 square. Equal 10 microsievert per hour also. Times S2 square, this distance. So S2 square equal this 4,000 divided 10. 400. This is a square. So S2 equal 20 meters. So the minimum distance is 20 meters. This is 20 meters. So we can walk here normally. So the minimum distance, if you can walk in 25, okay, it's good. 30 is better. But cannot go here if you walk normally. So now it is 20 meters. So in case if we need to the minimum, put that those limit here. But take care about units. Must be the same. Maybe some of us maybe ask conversion 4 millisievert per hour to micro. I will write this. I will do this. Okay, 4. I need micro. I don't need M. So remove M. It is 10 to minus 3. I need to put micro now. So now I don't need M. I erase it. Put number. So this is now sievert per hour. But I need to put micro. Okay, you can put micro. Divide it by micro. Sievert per hour. Now, this micro is 10 to minus 6. So it is 4, 10 to power negative 3, divided. This micro is 10 to negative 6. Micro, this one, micro sievert per hour. 10 to power minus 6. The above it will be 10 to power 6. With negative, it will be 4, 10 to power 3 microsievert per hour. 4,000 microsievert per hour. Move M, negative 3. Put mu and divide by mu because I need mu. And this mu is 10 to minus 6. Now you have 4, 10 to power 3 microsievert per hour. As we said.
Dr. Salam alaikum.
Salam.
If you can just repeat the last step we have done to have the 20, because after 400 I don't know exactly what we have done.
This one?
After the 400, what we have done to have 20.
Yes. Now, bring now this is square. This is square. S square. Now we need to say S according to square equal 4,000 divided 10. Well, this is the 10 microjoule per hour. This is 4,000 microjoule per hour. Now, and this is now S square. It is 400. But this is a square. So S according to is the square root of 400. It's equal 20 meters. Why I say meter? Because here, distance here is meter. So the result will be at the same unit, meter. Clear?
Yes, yes, clear. Thank you.
In exam, usually he give you combination between time and distance. Like this. Assume this is a source now. This is a source. And I need to make some maintenance in this source. Now, as a radiation worker, I need to do some maintenance here. Okay. Let's take some numbers. Okay. I have two procedures. To do this. The first one is, the first procedure number one, to do the maintenance. I can do the maintenance here and I take 10 minutes, for example. 10 minutes. Doing this work. And during this 10 minutes, I will receive, let's say, 200 millisieverts. During the 10 minutes, this is joules, this is not dose. I say that total dose I will take during this work, I will get 200 millisieverts. Okay? And the distance between me and the source in this case, distance for this procedure, let's say 10 centimeters. So I will be so close to fix, to this assembly, make something. So I will close to the source 10 centimeters. Deal with the source and the distance 10 centimeters. Through close or whatever, 10 centimeters. I will take 10 meters, 10 minutes working time. And at the end of the finish of this task, ending the task, I will find the dose that I received 200 millisieverts. This I can't accept. I need now to find another procedure. Assume I suggest this second procedure. I can do the same work, but I will use another tools. And this time, the time of working, assume the time is 20 minutes. I will take 20 minutes. Instead of 10 minutes, I will take 20 minutes. In this second way to do the same work. And now, the distance, I will use ton, for example. Assume the distance increase and become 2 meters. The time will be increased, 20. Distance also will be increased to become 2 meters far away from the source. That's good. What will be the dose? I will receive If I apply this, now, how we can solve this problem? As you see, time is changing, distance is changing. So now, we need to know what is the dose he will receive during this 20 minutes in this second procedure. Okay, to solve this, we know that dose increased when I increase time. When I increase time, dose increase. I increase time, dose will be increased. And I know the second thing that dose will reduce when I increase the distance. I know. When distance increase, dose decrease. So I have now two opposite ways. Now let's now solve it. I will write all this information here. In minutes, 200 millisievert as a dose. This is not dose rate, this is dose. And 10 centimeters. Okay, so now I am working, and this is the source, and this is that 10 centimeters. Now, the other way I will work in this 2 meters. And the time will be 20. Time will be 20 minutes. I ask what is the dose I will receive, not dose rate, dose. Now, this is at 10 centimeter, this is information. At 2 meter, this is information. Okay. Now, as you see, we have here distance, remember this, d dot 1 is 1 square equals d dot 2 is 2 square. I know the distance, 10 centimeter. This is 10 centimeter. 10 centimeters, I know the distance at this point. And dose rate, I don't have dose rate here, it is dose. But I can get it. As you see, I can get it. I have dose and time. So I can get the dose rate here. The dose rate here is 200 millisievert divided 10 minutes. So the dose rate is this one, is 200 divided 10 minutes. So this is now the dose, millisievert per minute. This is now dose rate. How many millisievert per minute? Dose rate here at point 1 equal 20 millisievert per minute. Now I give the dose rate as the point number 1. So I will write dose rate at point 1 times the distance at point 1 square equal. I know the distance here 2 meters. So I can calculate dose rate at point 2. Let's do this. So I will put here 20. This one. Right. What is the distance? 10. Take care. Centimeter. Centimeter. Equals. What is the dose rate here? I don't know. Times. What is the distance? This is 2 meters and this is centimeter. Now convert this 2 meters to centimeter. Must be the same units in both sides. So it is 200 centimeters square. So I can say this is 100 times 20, it is 2000 equal dose rate at 0.2 times, this is what? 4 and 1, 2, 1, 2. Okay, now, this 0, 3 zeros with 3 zeros. This 2, 1, this 2, 2. So now, dose rate at 0.2 is equal to what? 1 over 20. 1 over 20 millisievert per hour. Why? The dose rate here is 20 millisievert per hour, which equal how much? It is equal 0.05 millisievert per hour. 0.05 millisievert per hour. This is
hour
the
or minute? Excuse me.
how much?
Minute
I
or
think
hour?
it is minute.
We have taken minute, right?
Yeah, yes, you are right. Yes, yes, minute. Sorry, minute. Okay, yes, good. That's good. Okay, keep you observe with me, So it is 0.05 millisievert per minute. This is the dose rate at this point. But I asked what is the dose here received. Now it's easy. I know that this person take each minute this value 0.05 microsievert, each minute. But he work 20 minutes. So I will say the dose at 0.2, not dose rate. This is dose rate. This is dose only. Equals 0.05 times
20 minutes.
20. Dose. It's equal 1 millisievert. So if he take the second procedure for work, he will receive at the end of this work only 1 millisievert instead of 200 millisievert. So I will adopt this procedure for the worker to do the maintenance work by this way, 1 millisievert. So again, as you see here, this is must be dose rate. Dose rate, not dose rate. And distance square always. And take care about it must be the same in both sides. Meter, centimeter, feet, yard. Here, dose rate, microsievert hour, millisievert per hour, same must be. So now this is how to solve problem like this. And usually in exam, if he bring time and distance, it will combine by this way. My question for you is, which is more effective, distance or time to use? Okay, we will use two. But in case of there is no option, I need to only to select between distance and time. Which one you prefer? Generally.
Distance.
Distance. One square. For example, assume this is 100 microsievert per hour. Now, in each hour I will receive 100 microsievert. Assume this is at 1 meter. Assume at 1 meter I received 100 microsievert per hour. Now, reduce time by half. Instead 1 hour. Now, let's say this 1 hour, okay, I will make it half hour. This dose that I will receive at the end of that half hour, it will be only 50 microsievert. This is the dose I receive after 1 hour. if I reduce the time, instead 1 hour, I will work only 50 minutes. So I will, instead of 100, I will get 50. 100 per receiver, I will get 50. Now, distance now. 1 meter, I will make it 2 meters. I will make it, instead of 1 meter, I make it 2 meters. Increase double. I decrease the hair half. Now increase double. Same ratio. Same ratio. Now 2 meters. Increase. Now this 100 will be 100 2 square. 4. I increased 2 square. It will be 25. So distance as effective tool is greater in effect than time. As a relation officer, I will use time and distance together to reduce the amount of time to achieve ALARA. Remember ALARA, as low as reasonable, achievable. This is now the effect of time and distance. Of course, we need to say this calculation D1 dot S1 square equals D2 dot S2 square. This is the source here, and between you and the source, between you in any distance, S1, S2, air between you and the source. This is air. There is no shielding air. There is no any shielding air. Only air between you and the source. Only air. Shielding will start at the end of this day. So this only if this is air between you and the source. If you put this inside shield, this is another thing. We will speak about it. For example, you have a nuclear device, you have a nuclear device like this. Okay, I will write it. I will. Assume this is your nuclear device. You find your nuclear device something like this. You put the source here, and you get radiation in this direction. Okay. Now, this is now between you and the source is air. Don't calculate in this side. We say the distance here, assume distance here is assume 20 centimeters. No, you have here shielding, but here you have only air. So you can calculate by our way. D dot 1 times S1 square equal D dot at the distance and the time T at the point number 2 times distance at point 2 square. This is, yes, we can do this. Air. Well, this is air. Here, no, this is a shielding. We will speak about it. Like for radiographic, if you have the source inside the projector, this is now you cannot calculate to use hand shielding calculation. But just you remove the source inside the guide tube, now you can consider the air. You can consider the air. Guide tube for the USA Global projector is not shielding. For selenium, yes, but this is another thing. So just move from the projectors, now become in air. Now, what is the time now? Okay, let's, because we'll speak about gamma, I need you to be fresh, because we have something heavy to speak about it. Let's take 15 minutes, and we'll start, inshallah, with gamma. Yeah?
Okay, Doctor, can you just please go back to the last paper that we have done in exercise? I want to write something.
This one?
Yes. You speak ALARA. You speak about the ALARA in this board. I don't get it actually.
Yesterday we speak about optimization, right? ALARA, right?
Yes.
ALARA meaning to reduce the dose that a person receives, reduce time, reduce number of persons, reduce the possibility or probability to get accident. How can I reduce the dose of person? If I make him walk little time and also with more distance, so I reduce. You can use distance, time to reduce the dose. This is two methods or way to achieve ALARA.
You mean by whether to reduce the dose or to increase the distance?
Yes, decrease the time and increase the distance. If you can, as a radiation protection officer, provide for the workers tools that these tools make him far away from the source and do the same job with the same efficiency, it will be good. If you can give the operator or the worker training to enhance his level, to improve his level, so he can do the work in less time, okay, it's good. So now you decrease time and increase distance to achieve ALARA. What is the meaning? To let him take a dose low as it is possible, as low as reasonable achievable. This is how to, yes, this is how to use time and distance to reduce the dose of a person.
Very clear. There was a case where happened our side that there was a radioactivity task in DT, and the distance and time was not achievable. So they have another approved way. They use collimator material.
Yes, wait a moment. Did you see this projector? This the presentation, this one?
Yes.
Now we said here the methods of reducing external radiation dose, you can use decrease time, increase distance, use shielding. This collimator, for example. We will speak about this collimator at the end of this course. Let's see this now. This is now. We will speak here about shielding. This one. So we will use also the third way to reduce, which is collimator, shielding, this one.
Okay.
Okay.
No problem.
Inshallah. So only, as you see here, we have three methods. Time, distance, and if you can make it 14, it will be good. If you can make to 12, it will be better. If you make it, can you make it by any method, training, whatever, you can make it 8, it will be the best way. So there is no target safe dose. First, must be lower than the limit. Second, use ALARA to reduce it to the value as reasonable as achievable. Sometimes, some companies, facilities, institutes, like for example, Aramco saying, okay, I booked 15 minutes, 15 millisievert. For example, you are third party, you're making a radiographer there, job for radiographer, as a radiographer there, saying, okay, provide me the doses each month for the workers, saying 1 millisievert per month, totally 15 millisievert. They try to adapt it to make it become lower than the limit. That's good. They use ALARA, for example, now. But target, there is no something called target, really. Must be lower than limit and as low as reasonable achievable. Okay, now let's continue with I will go to the board now, so I will keep the camera in the board. Let's now continue. With the estimation of those rates from gamma sources. From gamma sources. As you see here, we have an equation. This equation is a relation between dose rate, D dot, this is dose rate, equal. This gamma is called specific gamma constant. When you write, for example, A in small letter, you write A and I will explain here. The dose rate from a source of gamma, if you know the activity of it, this is the activity of the source. If you know the activity and the distance between you and the source, always distance is inverse with dose rate, inverse. This is in the denominator square. Always square. Dose rate and distance are inverse square. Always you will find in the denominator and the square. So if you need to know the dose rate, like this situation, this is gamma. Now we speak about gamma. Specific source is gamma. This is gamma. And between you and the gamma and the source is A, still A. But you know the activity. And you know the distance between you and the source. Now, we have here a constant called specific gamma constant. This is a specific gamma constant. If you multiply this specific gamma constant by activity of the source divided by square, you get dose rate. Now. When you write, for example, letter A, this is a small a. And capital, you write like this. This is a capital A and a small a. Now, for gamma, this is a small gamma. And this is capital gamma. This is a small gamma. This is capital of the letter gamma. So we have here capital letter gamma. This is gamma specific constant. It's a constant. It is a constant. We speak about gamma, we put the specific gamma constant. Okay. This is the equation. But we need to speak about this in detail, this equation. Dose rate equals specific gamma constant, activity D squared. Now, if you apply here in this equation activity in megabecquerels, if you apply activity here, this one in megabecquerel, put the value in megabecquerel, and distance in meter, we have a table, give you this gamma constant with a certain value. And this dose rate will be in microsievert per hour. Again, this is the equation. There are some restrictions here. If you put here activity in megabecquerel, What is the source that you have? Let's say 50 curie. No, I won't use curie. I will use megabecquerel. Okay, if you put here, this is in megabecquerel, 5 megabecquerel, 10 megabecquerel, and distance in meter, you will select this from a certain table, we will see now. And this dose rate will be in microsievert per hour. In microsievert per hour. For person who use radiography, does not working with megabecquerel, used gigabecquerel. So now we have another situation now. In case if you will apply here activity in curie, distance in also meter, you have a table to select this from it. We'll see this table now. This constant. You will have certain value from table. This D dot will be in Rontgen per hour. Rontgen per hour. So now we have two cases. If you need, this depends on you. It depends on you. If you use activity megabecquerel per distance meter, there is a table. You can bring this gamma from it. You will calculate this rate in microsievert per hour. The value here will be in microsievert per hour. If you use activity, depending on you, in curie, distance in meter, we have a table again to select this one. Yeah. Those rate will be Rontgen per hour. This is dose rate. This is what? This is exposure rate. This is exposure rate. So this is what? Dose rate. This is exposure rate. But before we go to the calculations, we need to speak about this exposure rate. Remember, when we speak yesterday about dosimetry, this is what? This is gamma source. This is gamma source. I receive here dose. I need dose. I don't need Rontgen. For the calculation, give you Rontgen. Take care. This is the exposure rate. So in exam sometimes say, this, if I use this equation in traditional unit, activity is curie, traditional unit, the result will be exposure rate, not dose rate. So in exam, say, if you use this in traditional way, traditional unit, this will be dose rate? No, this is exposure rate. If you use the SI unit, and I will speak about becquerel, this will be also an SI, sievert. So now, this is dose rate exposure. Now, we speak about what? This is for gamma sources only. Now, this is the Rontgen per hour here. If I use the curie. Remember yesterday, we can say, remember, one Rontgen is equal 1 rad. Yesterday, we said this is for, one Rontgen equal 1 rad. For tissue, for human being, yesterday we said this. It is equal exactly, equal to 9.6. But we say, you can say 1 rad, 0.96 rad. And we say, we can consider 1 Rontgen equal 1 rad. This is absorbed dose. This is absorbed dose yesterday, absorbed dose. Now let's convert it to equivalent or effective dose now. 1 rad, and this is gamma. What is that? radiation weighting factor for gamma 1. Radiation weighting factor is 1. So 1 Röntgen for gamma equal 1 rad equal 1 RIM, because 1 rad times 1 radiation weighting factor is 1. Is 1 RIM. 1 RIM. So we can say here, we can say the value here, it will be equivalent to RIM per hour. The value that I will calculate it here, it will be Röntgen per hour, this is theory. But also it's equivalent to RIM per hour. Why? Because this is gamma source. 1 rad, 1 RIM equal 1 rad. For gamma, 1 rad, still 1 RIM. Why? Multiplied by 1. So I can say this is exposure rate equivalent to RIM per hour. RIM and Röntgen. Röntgen per hour for gamma is the same as RIM per hour for gamma. So now let's summarize. To determine the dose rate, if you know the activity and the distance, now you can do two things. If you use the activity in megabecquerel, distance in meter, this will be microcycle hour. If you use the Curie, distance squared meter, you will get Röntgen exposure rate per hour, which is equivalent to RIM per hour. Now let's go to the slides. I will keep also the camera in the flipboard, so flip chart, so I will keep it here. Only I need something from here. Okay. Did you see this? Yes.
Just before you go from there, the physical meaning for the exposure rate and dose rate.
Wait a moment, please. Okay, I will explain. Give it us. Okay, I will explain. Let's finish from this. I will explain everything. I know this is coming exam. Okay. Let's first take this number now.
Thank you.
I will explain now. Now, as you see here, we have different sources of gamma. All these are gamma. Cesium 137, cobalt 60, gold 198, iodine 131, iridium 192. All these are gamma sources. Okay. Now, this is the gamma specific constant. This is the gamma. This is a constant that we have in the equation. As you see, we have two values. For cesium, we have this value and this value. Cobalt, we have this value and this value. Now, depends on you now. If you used activity in megabecquerel, as you see here, in megabecquerel, use this value for cesium, use this value for cobalt, use this value for gold. If you used Curie, this one, you use this value for cesium, this value for cobalt, this value for gold, and so on. So now, this gamma constant depends on the unit that you select for activity. You select, it's depends on you, as you like. But take care, if you select megabecquerel, this one, megabecquerel, this one, as you say, you now have dose rate in micro, as you see, microsiever per hour. If you use the Curie, as you see here, this is a Curie, you will get Röntgen R per hour. Röntgen per hour. Now, is there a relation between these two values? Yes. If you multiplied this 0.087 for cesium multiplied by 3.7, 3.7. Remember Curie, 1 Curie equal what? For becquerel, equal 3.7 10 to the power 10. Remember this number by this way. If you multiply here 3.7 by this number, you will get this number. If you multiply for cobalt, for example, 0.356 times 3.7, you will get 1.32. So there is a relation now between them. If I know one, I can get the other. In this unit, I know this, I can give this in the other unit if I need to use Q. If an exam gives this constant, for example, for you, in megabecquerel saying the decay constant is 0.087 for cesium in the unit of microsievert meter square divided hour divided megabecquerel, and I need to use, not megabecquerel, I need to use Q. Okay, multiply this by 3.7, you get the other, and the calculation will be Rontgen per hour. And as I told you, we can say this is REM also per hour. Because 1 Rontgen for gamma is 1 rad is 1 REM. So we can say this is also equivalent as REM per hour. Okay, now, what is the meaning of these values? What is the meaning of this value? Really, this value has a physical meaning. Let's explain in the book. Assume this is your source of gamma. You know the activity. You know the distance. And you are staying here. You don't have radiation detector. And you can use this formula, this equation to know what is the lose rate. So if you know the activity, and you don't have the meter, you can estimate what is the dose rate here at a distance. You can say dose rate equal gamma, because you know the source, cesium, cobalt, whatever, iridium, you know the source. From there you can get this. And there are many applications in the store, app store, for example, have some application used directly to calculate. Okay, this is the times activity D squared. Now, what is the meaning of this? If you stay 1 meter, only 1 meter from the source, your source, and the activity of your source is one, assume megabecquerel. I use the megabecquerel. So the source activity is what? 1 megabecquerel. The distance between it and the source is what? 1 meter. The dose rate here is the gamma constant. From here, both activity 1 megabecquerel, both distance 1. Dose rate will be the gamma. So if you now have a detector, assume you have a detector now, your source is 1 megabecquerel, distance is 1 meter, and this is cesium. This is cesium, 1 megabecquerel. This is 1 meter. Your detector will read this number, 0.087 microsievert per hour. This gamma constant. This is the dose rate at 1 meter from the source that has activity, unit activity. What is the unit here? 1 megabecquerel. Here, for this number, for cesium, still with cesium. Now I use Curie. This is the dose rate. This is the exposure rate. This is the exposure rate, 0.325, this constant. This is the exposure rate of a source, 1 Curie. My unit now is Curie, 1 Curie at 1 meter, If the source is 1 Curie and I am standing 1 meter away, the radiation detector will read 0.325 Rontgen per hour or REM per hour. This is the meaning of a specific gamma constant. It is the dose rate for unit activity at 1 meter away from the source. So now, hold the equation as you see. The dot gamma, if this is the unit, and if this is 1 meter, now dose rate equal gamma. This is the dose rate. 1 meter, 1 minute. If this unit megabecquerel, this will be gamma, this microsievert per hour. If this is Curie, this will be Rontgen per hour. This is
Doctor?
yes. Yes.
The detector detects now. Now we are speaking of gamma only, huh?
Yes, yes, this is gamma. This is gamma. This is gamma sources.
And there will be for alpha and beta.
No, we will speak about beta, neutron, alpha, later. The next slide will be for beta, and the other will be
Okay.
we will calculate the dose for any type of source, but let's start with gamma. Okay. So now, let's now take example. A source of now cesium. I speak about cesium 137 gamma. Activity is, let's say, 50 millicurie. Activity 50 millicurie. What is the dose rate? What is the dose rate in microsievert per hour at a distance 2 meters. I now know activity, I know distance, I know time, cesium. Can I calculate dose rate? Yes. Dose rate equal gamma. This depends on type of source. This is depend on type of source, and I know the type of source. Times activity divided d squared. Now, he asked in microsievert per hour. It will be good if I take the unit that gives us microsievert per hour. To do this, you need to put activity in megabecquerel. Now, assume, no, I will not use this. It's depend on you. It's depend on you. So you can use here, put in curie, convert this, put 10 minus 3, and now directly put curie here. Distance, directly 2 meters. Take this gamma from the table, according to this unit, and calculate this. This will be Rontgen per hour, which is rem per hour. You can convert rem per hour to microsievert per hour and finish. So depend on you. Okay, let's take. Okay, because we asked in microsievert per hour, let's now use this is in megabecquerel. Okay, now dose rate. This for megabecquerel will be 0.087. 0.087. 0.087 from table. You have this table in data sheet. So now it is 0.087. Now activity must be in megabecquerel. Let's convert here. 50 millicurie. I don't need milli. Move it. I don't need. I need megabecquerel. Now let's go further step. This is 50. Move milli. It is 10 to minus 3. Now, this cancelled now. Still have curie. Now, this is the curie. 3.7, 10 to power 10 becquerel. Now, it is becquerel. I need megabecquerel. Put M and divide it by M. So, I will now. Now, I will put M here and divide it over M here, which is 10 to power 6 million. I will put here 10 to power 6. Now, let's 10 to power 6. Above, it will be 10 to minus 6. With this, 10 to minus 9. With this, it would be 10 only. So it is 3.7, 3 or 3.7 times 50. 3.7, I will put here, it is 0 over this 50, 5 times 7,
1850.
it is, okay, 1850 megabit. This is now converted to megabit. Distance is 2. Take care. Some of us forget to put square. 2 directly. So this is square. Now we can calculate now how much is this?
40.23.
40.23.
Yes.
40.23.
Yes.
What? This is megabit. This is microsieverts. This is microsievert per hour. Direct application. Only take care about this. Select Curie 1 thing per hour, which is rem per hour also. Select megabit. This is microsievert per hour. If you wish, you can like in Curie. Let's say, let's try this Curie also. Why not? Okay. It is 50 millicurie. I will again solve while the other way. Gamma times activity distance squared. Now let's use Curie again. 50 millicurie goes there. Now I will put now specific. Now I will select, but this now is convert to Curie. Okay, 50 milli, move milli, 10 to minus 3. 10 to minus 3. Now it become Curie. 50 milli Curie. Okay, now move milli. Okay, 50, 10 to minus 3 Curie. I will take it as it is. Now distance is 2 square. Now what is the constant here for cesium? It is 0.3325. Because I used the Curie. From here you can select this Curie. Did you see this? Okay. 0.325. 0.325. 0.325. Now it is Rontgen or rem per hour. What is the value here?
4 times 10 to the power minus 3.
4
Times 10 to the power
minus 4. Minus 4, how much?
3.
3. Okay. Rontgen per hour. It's for something here, like this. It's 40, it says 4023 times, put here 0.023, 10 to minus 3. Okay, now, it is now Rontgen per hour, which is rem. Okay, I will start now. Rem, this is Rontgen per hour, which is equivalent to rem per hour, as we said, because this is gamma. If this is neutral, no, at all. This is gamma, so it is rem per hour equivalent. Let's say equivalent like this, not equivalent. So now, I need to convert to microsievert. Okay, I don't need rem. I will convert it to sievert. Now, 4, 10 to minus 3. I will take step by step. Now, instead of rem, I will put now 10 to minus 2 to become sievert per hour. Because I know rem is 1 over 100 sievert. 1 sievert equal 100 rem. So 1 rem is 1 over 100, which is 10 to minus 2 sievert per hour. I need to put micro. Okay, keep everything now. 4, 10 to minus 5. minus 5. I need to put nitrogen. What nitrogen? Seaford where out. But you divide it here by nitrogen, which is 10 to minus 6. Above, it will be 10. Above, it will be 10. 10 to minus 6. Minus 5, it is 10. So it is 40 micro sievert per hour. What is the value here? 4. The same thing. So if you wish to use this or this, it depends on you. But select the correct gamma. Which gamma? Okay, this is how to solve a problem like this. Now, also we have, okay, keep also the camera in the board. We'll turn now, 1 minute. This is an example. Now, sometimes in exam, asking to calculate this gamma. Asking to calculate this gamma. Calculation now. In exam, if we ask it to calculate gamma, really for me, I will go to the table, he will say, what is the gamma for cobalt, and give you some information. I will go to the table that we have in formula sheet and bring it. I will not calculate. But let's now know how we can calculate it. We have this formula. Also in exam, give it to you, this formula. To calculate gamma constant. But this is in SI unit. So when you calculate using this formula, you will have these values. This one. This in this way, in SI unit. So you will calculate these values. For cesium, you will calculate this by using this formula. What is this formula? Gamma equal 0.14210 times F1E1 plus F2 F. Okay, let's now take an example here to explain, and I will now return to the board. Okay, this is, for example, cobalt 60. This is the cobalt 60. Remember when we say it emits by beta and the daughter nickel is excited state, it will give you gamma. So this is gamma source. Okay. He mentioned here, as you see, it will give you 2 gamma. We spoke about this before. 1 decay of cobalt will give you 2 gamma, as you see here. Now, what is the energy of this first gamma? 1.173 million electron volt. And all the gamma will come and reach to this state. And now, also gamma will come from the first state to the ground state. What is the energy here? 1.332 million. Must be in million. As you see here, 100%. What is the meaning of 100%? If we have 100 daughter of nickel here, 100 will go here. There is no any internal conversion. And now we have 100 of daughter in first excited state. 100 will go here. So all the daughter here will give you gamma. All the daughter here give you gamma. This is 100%, 100%. Remember for cesium, this is beta decay for cesium. Now this is a daughter in excited state. Now, here we have a value 94. We will say before it is 85. I say yes, it's 85 as a number, but the branching ratio here is, we speak now about doses. So this conversion electron for the internal conversion will add some dose. So you will find here, this is 94. We speak now about doses. So this value will give it in exam. This value is given for exam. We will write something like this. Take this value. This is the F. This is the F. This value is the F. What is the energy in MEF? This is the energy in MEF. This is the energy in MEF. Let's now take this example to solve. This is for cobalt. How to use this formula? Gamma for cobalt 60. It is 0.142 times. How many energies we have? Only two. We have two. So I will open here these brackets and I have here two things to add. What is the first energy? Value in MEF. What is the second energy? Value in MEF. Branching ratio. All the water will give you gas. So it is 100% here. This is the ratio. This is the ratio of the second. For gamma now, 0.142 times 100% meaning 1 times. What is the first energy? 1.173. 1.173. Now the second, 100%. We mentioned this 1. In exam, if we give you something like this, we will mention all this data. Times, what is the energy? 1.33 or 27, I think. I think this is 1.33.
2.
1.17, 1.33. This is here is wrong, I think. This is 1.332, okay, whatever. This is 1.17, 1.33. We'll take this 1.17, 1.33 to make it easy calculation. Now, 1 times this is the same, 1 times this is the same. So I will add 1.17 plus 1.33 multiplied by 142. This is 2.5. So 0.142 times 2.5. Take care here. This must be MEF. In exam, if we give it you in kilo electron volt, you must convert to be MEF, million electron volt. Multiply this now, you have 0.335. 0.335. If you return back to the table, this table, if you return back to the table, you will find cobalt, this value. This value. 0.356, and we have here 0.335. It's 1.3, okay. Almost the same estimation. This is the value.
دكتور
Yes.
يعني بالاختبار ممكن نحسب هذه الكونستنت وهي already given في
Yes, yes. In exam, saying, for example, I think I have problem like this. I have problem like this. In exam, he may say, we have a source. Say, we have a source with the following chart. This is the source. He gives you the source, for example, beta. And now saying, let's take an example. Assume the following. That we have a source, I don't know, it's X. And decay by beta. Give you delta. Give you this chart, for example. Now, gamma. Assume something like this. This is Y. Delta Y. And to remember only, if this is Z and if this is A, this is beta minus, this is Z plus 1, remember, and this is still same atomic number. Same mass number. Remember, this is 1. To remember only. This is a total. And excited now. Give you gamma, assume, let's say take this number. 700 kilo electron volt. 1 million electron volt. 1,500 kilo electron volt. Ratio, I put numbers, roughly 50%. Ratio 100%. Ratio, assume, I say something, 30%. Something like this. Or we say gamma equals 0.142 times the first radiation. What is the ratio? 0.5. 50% meaning 0.5 times. This is 700 kilo electron volt. Must be a million electron volt. Move this 10 to the power 3 divided by m and multiplied by m, mega. So now it will be 0.7 million electron volt. Plus, now I add. This is 100, meaning 1. Times. This is 1 million. Okay, million, okay, I will take it the same. Plus. This is 30%, 0.3. And this is what? 1,500 kilo electron volt. Must be in million electron volt. I will divide it by 1,000, so it will be times 1.5 million electron volt. 1.5 million electron volt. Now, multiply this, it is 0.35 plus 1 plus, this is 4.5. Now, multiply by 142, this is the gamma. If you calculate this, multiply by this, you will find here value. You will find here value. This value in SI unit, microsievert per hour for each megabecquerel at 1 meter. This value.
Boss, last value is 0.45, not 4.5.
This one?
Yeah.
Yes, okay. This is the 0.45. 0.45. 0.45. Now multiply this, you get number here. This is in SI. So if you use this in the equation here, if you take this number, this must be in megabecquerel. This must be in megabecquerel because you calculate this in SI unit. So use this in megabecquerel. If you need to convert to traditional, Rem per hour or Röntgen per hour, multiplied by 3.7. Multiplied by 3.7. You have in the Röntgen per hour.
Doctor, please. Doctor?
Yes, please raise your voice because it's very weak here.
Can you just repeat how we convert the percentage of energy here to the 0.5, 0.7, because still I didn't get it. I know how to calculate the dose rate, the way, but still I didn't get it, the reason, the main reason.
This one?
The 0.5, the 0.7.
This
0.5,
one?
how it came.
This is 50%.
Okay.
50%. 50% meaning 50 over 100.
Why we need to do this conversion?
Because this is the fraction. I put here, this is number. I need number here. This is fraction. Okay, put it 50% here, but in this form. 50% take it, but put in this form. 50 over 100, which is 0.5 or half. We put here the fraction. We put here We put here, for example, this is assume here, we have here 500 atoms, deuters. Only 25, only 250 make gamma. And because this is 50, half of them make gamma, half of them make internal conversion. So only I take this 50. And here we have 250. All will make gamma with this. And when we reach here, 250, 30% only make gamma and 20 make internal conversion. So here, half.
Very clear.
Now, this is how to calculate those from gamma sources. For beta sources now. Dose rate equal. Now, let's see in the slide to be the same. Now this is for beta. As you see, we have the same equation, similar equation. This is 5. This is a constant. Instead of gamma constant, we have 5 here. We have 5. Consider this 5 as the constant. 5, constant. Now, this is the activity. This is the average energy. Average energy. This is the distance squared. As you see, like gamma, constant but 5. This is activity. This is distance squared. Only I put here E average, more. I added E average.
Excuse me, sir.
Yes.
Sir, these formulas will be available in our question paper.
I can't hear you. Could you please far away from the microphone because it's repeated.
Sir, the given formula for dose rate, these formulas will be available in the question paper.
In exam?
Yes, sir. Yes, sir.
In exam, yes, you will find. In exam, you will find the following. You will find estimation of dose rate from beta. D dot equal 5 times activity E average D squared. And in exam, you will find this where D dot is the effective dose rate in microsievert. A is the activity. You will find this exactly in exam, this slide.
Okay, sir. Okay, thank you.
Okay. So now this dose rate equal 5 times activity E average. This is the energy, average energy, and D squared. Now, there is no option here to select 4 units of activity. Here, there is no option. In gamma, megabecquerel or curie, as you like. Now, here, this activity must be in megabecquerel. Must. If you have in curie, in millicurie, you must convert to megabecquerel. Distance in meter. E average energy of the source, this is must be in million electron volt. This is only the restriction here. Must be in million electron volt. Then this D dot dose rate will be in microsievert per hour. Must be like this. This is megabecquerel. This is distance in meter. This energy in million electron volt. Then this dose rate will be in microsievert per hour. You calculate and give number in microsievert per hour. Now, sometimes we don't have E average. We don't have E average. He give you E maximum energy of beta of this beta source, maximum energy. Now, if you divide this maximum by 3, you get E average. So E average equal E maximum divided 3. E maximum divided 3. And you here apply for average, So if you have average, put it directly, but in million electron volt. If you have E maximum, divide it E maximum by 3 and put here in million electron volt also. Let's have an example.
Victor, please.
Yes.
For the effective dose, is the
Yes.
case here similar to the gamma if you want to have it in
Yes, now
per hour?
we calculate the effective dose rate.
Yeah, I mean, does the case similar to the gamma if you want to have it in a classic way or SI unit?
No, there is no option here. You must. This is now, I told you, it's a must to put activity in megabecquerel and energy in million electron volt and the distance in meter. Then the result of this rate will be in microsievert per hour. Now, D dot is 5 times activity times E energy average divided distance squared. Now, this microsievert hour, this million electron volt, this megabecquerel, this distance, no other option for activity to be Curie or whatever, must be megabecquerel. Now, why we say we average? Remember when I told you, if this is the beta source, some beta has very low energy. Some beta has another energy. Other beta, more energy. Other beta, we have the source give you different energies for beta that this source emits. As you see, some beta lower, some beta higher. And there are a maximum value cannot exceed. This is called E maximum. Remember this when, as I told you, if this is a nucleus, decay by beta, it gives you beta and also give you antineutrino. Remember this antineutrino? I told you we have here energy, must release completely. This energy may be some given here, some given here. Sometimes this take all the energy and zero here. Sometimes this take all the energy beta and put zero here. So this is the maximum. When beta take all the energy and go out. So this is a maximum. Now we need to calculate for the average. So we need the average. The average is average, which is this equal E maximum, this divided 3. And we used here the average. Now let's take an example. But before example. Now, this is the low beta energy. And I'm standing here. Assume I'm standing here. This very low energy will not reach to my body. It will stop there. This will stop there in air. This is air. So the low energy beta may stop before to reach me. If I far away, all this beta will not reach. Only this will reach to my body. If I stay here. If I stay here, only maximum, almost the maximum will reach. So some beta may absorb it in the air before reach to me. Also, some beta may absorb it in the dead layer skin. Dead layer skin will not go to the living tissue. So in case of exam, say something like this, we will inshallah know how to deal with it. But first of all, now let's use this to calculate. and we will take this is now later into consideration. But now the dose rate 5 times activity, E average D squared. Assume we have a source, pure beta source. This is beta, pure beta source. An example will say this: you have a beta source, and asking for that dose rate with E maximum 900 kilo electron volt and activity equal 100 millicurie. What is the dose rate? What is the dose rate in milli rem per hour? I make it general. I don't know. He asked me what is the dose rate in milli rem per hour. Okay, this is beta source. I know E maximum, I know activity. What is the dose rate? At a distance equal, let's say, 150 centimeters. 150 centimeters. Now, let's apply the equation. 5 times activity times E average divided D squared. D must be in meter. Must be in meter. So this would be 1.5 meters. First conversion must be in meter. Must be in meter. 1.5 meter. So I will put here 1.5 meter. Now, E maximum, not average. E maximum, 900 kilo electron volt. Now let's make each thing, okay, 150 centimeter must be converted to 1.5 meters. This is the first one. Second, this E maximum, I need E average. I need E average. It is E maximum divided 3. It is 900 divided 3. It is 300 kilo electron volt. It must be in million electron volt. It's equal 0.3 million electron volt. Kilo, million now. Maximum, average now. It's average. Okay. So now this is the D. This is the E average in million electron volt. Now activity. It is in millicurie. It is in millicurie. I need to put in megabecquerel. Now activity. It is 100 milli. Move milli. 10 minus 3. Curie, move curie, put in becquerel, 3.7, 10 to power 10. Now it is becquerel. This is becquerel. I need in megabecquerel. Okay, put M divided by M. I will divide it by M here, which is million. M is million. 10 to power 6, million. Million over million. Now, this is now 10 to minus 6. Up, above. It will be 10 to minus 6. See now, it is 10 to minus 3, to 10 to minus 6, minus 9. With this, 10. So this will be 37 times 100. It is 3,700. 3,700. So activity will be 3700 megabecquerel. Now, activity in megabecquerel. Put here. Average in minute. Put here. Distance in meter. Put here. Let's now solve this. Use rate 5 times 3700 times 0.3 divided 1.5 square. Now this number is microsievert per hour. This is the condition for this equation, microsievert per hour. Okay, can you please calculate this? Can you please calculate this?
2,466.
Number by number, please. Number. What is the first, please?
2,
2,
4,
4,
6,
2, 4, 6.
another 6.
This one?
Yeah.
Okay. Microsievert per hour. This is the value. He asked it in millirem per hour. Millirem per hour. Remember another way for transport index, we can do it, but remember for transport index, we say if you have number in millirem per hour, you can put in microsievert per hour. If this is microsievert per hour, divided by 10 to get this. If you get this, multiplied by 10. Remember? Yesterday, remember? If it is millirem per hour, take it as a transport index. If microsievert per hour, divided by 10 to convert to millirem. So now microsievert per hour, to convert it to millirem, multiplied by 10 millirem, if this is micro, divided by 10 to convert it to this. So now I will divide this by 10 to get in millirem per hour. Divide by 10 to get millirem per hour. Let's apply even here. Now, micro I don't like. I don't need. 10 to minus 6. Sievert per hour. Sievert per hour. I need to put milli. Okay, put milli. Put milli and divided by milli. And we need to move this sievert. Okay, I will write 2, 4, 6, 6, 10 to minus 6. Now, milli, I need to remove this to put rem, but to put rem, I need to multiply by 100 here, because one sievert is 100 rem. So millirem per hour. And put here 10 to minus 3. This is M small. Now, if you go up, this is here would be 3. This would be 3 above. 3 was 2, 5. And this is minus 6. So it will be 246.6 millirem per hour. As I told you, divided this by 10. If this is micro, need to put in rem, divided by 10. So now this is the value in millirem. We'll make now general example, as I told you, give you everything in different units. Instead of megabecquerel, instead of kiloton volt, instead of meter, and instead of microsievert. So calculate and reach to microsievert per hour, then convert. Now, let's take our example to take into account the effect of absorption of beta in air, and assume we have a source of beta, emit the activity is 5 megabecquerel. Distance is 0.5 meter. E average equal 0.5 million electron volt. Everything is a suitable unit. Now, I will add something here. Assume that 5% of beta, 5% of beta absorbed in air and dead layer of skin. People, what is the dose rate of this source? This is the information. Assume that 5% of beta absorbed in air and dead layer of skin. I will calculate by the same way. I will not take this into account at all now. At all. Forget it. Dose rate 5 times activity megabecquerel 5. Average is 0.5 in million volt. Distance is 0.5 meter squared. So now I have microsievert per hour. Now this is 5, this is 5 times 5 times 0.5. This is with this 0.01, with this, now we have here 50. This is 50 microsievert per hour. Forget this at all, don't think in this now. Calculate normal, 50 microsievert. He say 5% of beta absorbed before to reach to the living tissue. Okay, so I will receive only 95%, which is 0.5. I will receive only as a dose 0.95. 5 in air outside of my body. So the remaining is 0.95 multiplied by 50. This one. So now forget this at all, calculate normally. Then when you finish, 5% absorbed in air. And then, okay, so I only absorbed in tissue, living tissue, 0.95 from this. So it is
74.5.
70.
I'm sorry, 47.
Yes, 47.5 microsievert per hour. So in case if you mention something like this, forget it. Don't think in it at all. Calculate normal. The remaining is 95. Assume 15% absorbed in air. I know there's no delay in air. Okay. 85. Assume we say 10% in dead layer. If we say, okay, 10% in dead layer, 90% in living tissue. Take the rest value and multiply by this value. In case if he mentioned something like this, if he didn't mention, okay, that's good. Put that 50. Put that 50. This is now how to calculate by B. I will make a summary now. For gamma, we have for gamma activity times for gamma sources, we have specific gamma constant times activity divided this square. Take care about this value. Why? Because according to the unit used here, you will select a certain number. Classic, you have this is the exposure rate 1 meter away for 1 Curie source. This is the value. Distance, meter. This is Q. If you select megabecquerel, this is the dose rate, not exposure rate. Dose rate. 1 meter away from 1 megabecquerel source. This must be megabecquerel. This is distance square. Now, for beta, we have 5 times activity times T average. And always D square. Always D square. Now, we have etc. more here, we can calculate it gamma, which is 0.142 times energy and diffraction, plus energy and diffraction, plus energy and fraction. Now, let's go to neutron now. Same thing. Same thing. Distance square here, always. Always. Constant here. The constant here is 0.8. Constant, constant, constant. Times. Now, we have here activity, activity. We have here intensity. Intensity. There is no source, decay naturally by neutron. We have intensity. For example, americium beryllium, they emit alpha, and alpha make interaction, give you number of neutrons per second. So we now have here number of neutrons emitted per second. Instead of activity, we have number of neutrons emitted per second or produced per second. Here we have number of atoms decay per second. Number of atoms decay per second in megabecquerel, or in theory, here in megabecquerel. Here, number of neutrons emitted per second, intensity, multiplied by conversion factor, C, constant also. Depend on the energy of the neutron. Depend on the energy of the neutron. So we have here similarity, constant. This is the conversion factor, like this guy, conversion factor. This is number of neutrons per second, and the same per second, not per minute, per second. Distance square, neutron. From where we get this value? From table, depend on the energy. Let's see in the presentation here, slide. This one. Dose rate, 0.08 times C. This is constant, depend on the energy. This is N. This is a neutron fluence in neutron per second, or neutron intensity. How many neutrons emitted per second from the source? This is distance squared. Let's see the C. Okay, this is the constant conversion factor. Depend on the energy. Depend on energy. Okay, could you please mute? I heard some. Okay. Now I mute it. Okay. Now this is the energy. This is the constant values you have. Let's take an example. Calculate the effective dose rate. We calculate dose rate here. 0.5 meter from americium beryllium neutron source that emits 3×10⁻⁷ neutron per second. This is N, neutron per second. Assuming the average energy of the neutron is 1 million electron volt. 1 million electron volt. Okay, this is the relation, dose rate, 0.08. Conversion factor depends on the energy. N, number of neutrons emitted per second. Distance squared. I have distance, yes, 0.5 meter. I have N, yes, 3×10⁻⁷ neutron per second. Conversion, what is the energy? 1 million electron volt. Let's return back here. 1 million electron volt. This is the C. This is the C. 1.32 10⁻⁴. Now, I have all information. C from table. N given. D given. Now multiply. This will be also microsievert per hour. Microsievert per hour. When we apply it, give us 1.27 10⁻³ microsievert per hour. As you see, it is direct application. And as we see here, depends on the conversion factor. you must bring this conversion factor from table, depends on the energy. So let's take an example. A neutron source emit 10 to power 6, 10 to power 8 neutrons per minute. What is that? Dose rate for this source at 150 centimeters. Average energy or the energy of this source is, let's say, 5 million electron volt energy. Now, dose rate equal 0.08 times C times N divided B squared. D here 150 centimeter, must be meter. N number of neutrons per second, their number of neutrons per minute, 6, 10 to the power 8. So I need now to calculate N. It is 6, 10 to the power 8 divided, this is per minute, divided by 30, now it becomes per second, which is this with one of this, it is 10 to the power 7 neutron per second now. Neutron per second. C, I will go to the table as you see here. Table 5 million electron volt, it is 1.56 10 to minus 4, 1.56 dose rate. Now, distance 1.5 meters, 0.08, 1.56 into minus 4. This is the C value times N, 10 to the power 7. Now, we can calculate it, and the result will be, number here will be Sievert per hour. If we ask it in millirem per hour, in whatever, you can convert this to that unit as you want. So as you see, direct application. We need only take care about units. And in exam, if he need to change something, he will ask about units. Take care about this. So now we started alpha, beta, gamma, beta, neutron. Alpha now. This is the source of alpha. I'm standing here. Few centimeter will stop alpha. There is no any dose here, 0. Even I am standing here in contact with this alpha. This alpha cannot penetrate the dead layer of skin. So there is no dose outside from alpha. All these equations we use for gamma, for beta, for neutron, external dose. We calculate external dose, source outside here. For alpha, the dose that I receive always 0. External, 0. So there is no need to calculate dose, external dose from alpha. Not applicable. But internal, yes. Internal, yes. and we will speak about internal, inshallah. So for external, for alpha, it is not applicable, because alpha represent internal hazard, not external hazard. Estimation of those rate from alpha particles don't penetrate and don't present an external radiation hazard. External dose calculation are generally not required, not applicable. This is for alpha. So for gamma, beta, neutrons, we can calculate the dose rate if we know the activity, what is the distance between us and the source, and type of source, like in case of gamma, to determine the gamma, specific constant gamma, and energy in case of beta to determine the average energy. Neutrons, we need only to know the energy to select the conversion factor. Now let's see some problem in exam. I have some messages in chat here. I will answer it, but when we finish and we start the break, I will speak, because it's speaking about norm and something like this. So now I will go to the models to see how the equations come. Model. Okay, let's see how this problem came in exam. Bismillah ar-Rahman ar-Rahim. Remember the problem that we calculate for distance at time morning 10 meter, 10 centimeter, 10 minute, dose is 200 millisievert, the dose, and he working with another condition 2 meters away, but increasing time. What is the dose that he received? This is the 31. This is the 31. And we say we need to calculate the dose rate first and apply the dose rate multiply distance square at the first point equal the dose rate multiplied by the distance square at the second point and calculate. This is the same. An operator is conducting a corrective action with a source located 25 centimeters from him for 10 minutes, and his dose will be 180 millisievert. If we can do the same action using a long handle so that the distance to the source will be 150 centimeters, but the time will be 15 minutes, then the incurred dose is, and we solve this tomorrow. We solve this one tomorrow, morning. We solve this in the morning. So let's go for number 32.
Excuse me?
Yes.
So in this case here, we will use only the distance and the dose and neglect the time. Am I right?
No. The time different now, as you see here, 10 minutes, and now it becomes 15 minutes. Okay, I will solve. Let's solve. You can do the work in 10 minutes, in the first case. In the second case, in 15 minutes. First case, in 10 minutes. In the first case, you will work, I think, to 25 centimeters, right? 25 centimeter. Yes, and in the second case, 150. 150 centimeter. In the first case, you will receive 100 millisievert. Now I ask the dose here, dose, how much? Remember in the morning I told you we will use D1 dot times S1 squared equals D as the second case, different distance, times S2 squared. And this is dose rate, this is not dose. He gave you here dose millisievert only. We need millisievert per time, and the time here is minute. 180 millisievert. In each minute, how much you receive? We will say 180 divided 10. So this is now the dose rate. Dose rate here is with 180 divided 10 millisievert per minute now. This is millisievert per minute, dose rate. Times S1, what is the distance? 25 centimeter, take care, must be the same to the other side, square, equal. Now, what is the dose rate? This one, second, the second point. I don't know. This is 2. What is the distance? This distance, centimeter, the same, okay, I can go now, because the same, square. So I can bring now this D dot. Dose rate at 0.2. It will be, now it is 180. 10 multiplied by 25 squared now. Divided 150 square here. So now let's see. This now was 25, this is 6. Was 25, this is 6. So now this is 6, this 0 with this 0. This 6 with this 3. This 6 with 3. This is 0.5 millisievert per minute. This is a dose rate here. In this case, dose rate. This is dose rate. But he asked dose. I calculate dose rate. D dot. He asked D. Dose rate. He asked him dose. Now, he worked in how many minutes? What is the time? 15 minutes. Each minute he received 0.5. So if I multiply 0.5 times 15, the dose rate multiply the time give you 0.5 times 15, it will be 7.5 millisievert. You will receive 7.5 millisievert during this 15 minutes. Let's take number 32. Return for inshallah for the board. Keep the camera. So 32. The effective dose rate from an exposed cesium-137 source of 3 curie activity at a distance 25 centimeter from the source is exposed cesium-137. The exposed meaning without shield. Exposed meaning bare without shield. Okay, now 3 curie, I have activity, I have distance, I have type of source, it's a cesium. Now I have table in the data sheet, tell me what is the gamma specific constant. Now we put the units in millisievert per hour and sometimes rem per hour. For us, no problem. Okay, let's now calculate by curie. Calculate by curie. I have curie here. I will. If you need to calculate by megapixel, it's depend on you. Let's now return back to see the gamma constant for Curie unit. How much? I will go now to the table. To the table here. Cesium. And I will use Curie, so I will use this. 0.325. 0.325. I will use 0.325. Okay, let's now return back to the equation, to the problem. Okay, number 32. Number 32, this one. Dose rate for gamma cesium equal. What is specific gamma? I will use 0.3, I think 25. What? 0.3? 0.3 what?
0.325.
0.325.
0.325, okay. I will use Curie. It is 3 Curie. This is why I take this. I didn't take 0.087. Why? I used the Curie. I didn't use the megapixel. If you wish, you use megapixel, okay. And change this. Now, distance is, the distance is
25 centimeter.
25 centimeters. Must be in meter. Must be 0.25 square. This is now in Rontgen per hour, which is rem per hour also. Which is rem per hour also. Let's calculate. And how much is this?
15.6.
15.50.6.
No. 1.5. 1.
1.5.
0.6.
Okay.
Yes.
1.5.6. It is 15.6. What? Huh? The K, we use the Curie. So it is Rontgen per hour, which is also rem per hour. Now I have this value. Now, the results now saying rem per hour. Rem per hour. I have rem per hour and I have millisievert per hour. Okay, now, as I told you, you can consider this one. You can consider this rem. You can consider this also rem per hour. Remember, Rontgen per hour is equivalent to rem per hour. Well, this is gamma. Now, I have this value 16.5, 15 point, okay, this number B, huh? Number B. This is that, give you in D. This is D. Let's, number 33. One of our friends asking about this gamma constant calculation. Now, this is 33. The gamma specific exposure rate, the gamma specific factor for Powell 60, which emits gamma ray with two energies, which are, give you now this, okay, we have here, mistake here, this is 1173, not 1273. So please, okay, but this is 1, this is 1173, not 1273, and 1332 kilo electron volt. Take care. He asking gamma specific constant in the SI system. You will calculate in SI system. If he asked in old or traditional system, calculate normally, then multiply it by 3.7. Remember this calculation gamma equal 0.142. Now, fraction 100%. He mentioned the energy. The energy here, huh? The energy here. He mentioned something about fraction. He didn't mention anything about branching ratio. He didn't mention 100% mean. 100%. So now it will be 1 times 1.173. This is what? Energy in mass, in million. He give you in kilo plus branching 1 also, because he didn't mention, times 1.33. Now multiply 0.142 times, this is 2.5. Multiply this value, you get in SI unit. In SI unit.
0.355.
0.355, which is 0.355. This is number D. D micro. Now we speak about Sievert, we speak about Becquerel. From the beginning, I will refuse A and C. From the beginning, I will refuse the A and C. Why? This is traditional unit. Curie, Curie. Rontgen, Rontgen. He said in SI. In SI, now Becquerel and Sievert. So something between A, which must be B or D. B or D. This is the only selection I have. And it is D. And it is D. Now, the dose rate, no, this is now shielding. Number 34, we will use the shielding. We will use the shielding. Number 35, internal dose 36. Yes, let's say number 36. Number 36. Also, we studied it before, but this also is the calculation of shielding, okay. To review only. We studied it, but to make a revision, if you know that, the attenuation, okay. Now, so it's now, yes, number 38. Number 38. This is good to remember. Number 38. And 39 also is now started, okay. Number 38. The best material to be used to make a shield for neutron from the following material is hydrogen gas. Number 38. Number 38. Did you see the slide? Number 38?
Yes.
Yes,
Okay.
yes, very clear.
Okay. Because number 38. The best material to be used. Okay, let's bring it down. The best material to be used to make a shield for neutrons from the following material is hydrogen gas, paraffin wax, lead, uranium. Let's make some comment about this. We said for the neutron shielding, we need 3 layers. 3 layers. First layer is something contain hydrogen, like water, wax, paraffin, polyethylene, whatever. For elastic scattering, to reduce the neutron energy, to moderate it, to slow down it, to thermalize it, so it becomes slow. Then we have a cadmium, only 1 millimeter from cadmium, metal sheet, to absorb this slow neutron. And as a result, for absorption of this neutron, there is gamma, we will emit from the cadmium. And we need a layer for shielding of gamma, which is lead. So we have layer about 25 centimeter from water, and layer from cadmium, which is about 1 millimeter, and layer of lead. Okay, this is the electron shield. Now, assume in exam I asked it. The shielding for thermal neutron is, and give you this: water, cadmium, lead. Cadmium, lead. Lead, cadmium. Lead, water, cadmium. Which one will you use? Shielding for thermal neutrons. Huh? You must say, okay, he said thermal neutrons, thermal, he's thermal neutron. He makes moderation. How? I don't know. But he makes moderation. He asking for thermal neutron. So I will use cadmium directly, then lead. There is no need for water. I don't need water. I don't need paraffin. I don't need wax. Why? I need water and paraffin to thermalize, to make thermal. But he said thermal neutron. So cadmium directly to absorb, then lead. Now, assume now in this question, 38, he say, which material you are going to select among this to make a shielding? Where is the cadmium? Where is the lead? Where is the... I have only paraffin wax. Lead, of course, no. Lead, of course, no. This equation, this problem, this question, he's mentioned this is the available material I have. So deal with this situation according to this. Don't say I need water, I need cadmium, I need lead. No, I don't have this material. I have this material only. Select among them. So now put yourself in his in his place. Only this material I have. I need to make a shield now. Okay, I will use this. Now lead, of course, no. Uranium, never. Now I have hydrogen gas and paraffin wax. Hydrogen is the best, but this is gas. This is gas. Very low concentration amount of hydrogen. So paraffin wax, this is now the only available material I can select. But in this situation now, I will tell him, I don't need 25 centimeter of paraffin wax. I will use greater than 25. I will use 50 centimeter thickness of this paraffin, 50. Why? I will put the source here and the 50 and the 50 paraffin from the 50 thickness. The thickness of paraffin will be 50. I will put 50 centimeter paraffin between me and the source. Between me and the source, 50 paraffin, 50 centimeter paraffin, not 25. Why? 25 will make thermalization. 25 will make thermalization, reduce the energy. And then another 25 to be as a shielding for absorption of neutron, and for gamma. I told you, if you remember, any material can absorb the thermal neutron, but I will select the best one, strongest one, cadmium, but I don't have. So now, used now paraffin, which contain hydrogen, this hydrogen will absorb the thermal neutron. Then the rest will be for gamma, because he asked, selected only one material here. Selected only one material, so paraffin wax. But now I asked him, give me 50 centimeter, 70 centimeter, either increase it. So 25 to thermalization and the rest to absorb and to make a shielding for gamma. So it will be B. Okay, number 39. Beta particles are emitted from a source with maximum energy 2.3 million electron volt. Give you the maximum. Then the maximum range of these particles in aluminum with density 2.7 give you in centimeter. Now, Remember how to solve this? Remember the range that we used for beta. We have two equations in case of the dose, if the E maximum greater than 0 and less than 2.5, we have a certain equation, and greater than 2.5 million volt, we have another equation. Now we will use the first equation, apply here, and we will calculate range in gram per square meter. Divided this by the distance, you will get values. Remember, we solved this, it was 0.41. Remember this one. Why I say take care about this? Because now we'll say beta, and we're asking, we know that we take two things about the beta calculation. Range, and this is one, and dose rate. In dose rate, we have equation. Range, we have the other equation, which is light shielding. Maybe he will ask you now, instead of saying, what is the maximum range of this particle, he will say, what is the minimum thickness of material, of aluminum material used as shield? Maybe he will say in the other word, what is the minimum thickness of aluminum as a shield? Minimum thickness of aluminum as a shield is the maximum range of beta inside this aluminum. Okay. Let's also go to the other model. Okay, now, if you know number 29, did you see? Okay, I will bring it in the. Number 29. If you know that the specific gamma ray constants for cobalt 60 is 1.32 Rontgen meter square divided H over Curie. This is now classic. Then the effective dose rate in SI unit. He asking in SI unit. In SI unit. At a distance 0.5 meter from the exposed cobalt 60 point source with activity, give you activity in megabecquerel. Is about give you now this option. Now, it's depend on you. You can convert this megabecquerel into Curie. Or keep as it is, megabecquerel. Wait a moment, okay, you can convert it to Curie and use 1.32, this value directly. This is for Curie. You can use this directly in equation, but you need to convert this to Curie. Or keep this as it is, and now this one, you can divide it by 3.7, you can divide by 3.7 to get this value in SI unit. It's now up to you. Use this Curie, this value as it is, convert this to Curie. Or keep this in megabecquerel and divided this by 3.7, so you now use the gamma specific constant in SI unit. Now it's easy now to calculate. If for me, I will divide this by 3.7. I will divide this by 3.7. Let's now solve it. What is that? Yes. Okay. I will now say Joules rate equal gamma times activity divided this square. He gives me this in traditional. I will vote it 1.32 divided 3.6. Now it's SI. Divided this by 3.7. Now this is now SI. Multiplied by, what is that activity? It is 1.85. 1.85 gigabit now I speak. 10 to the power 5 megabit. Now divided D. D is 0.5 meter. Calculate this. It will be microsievert per hour. What is this calculation? Can you please calculate this? Point 5 centimeter. Yes, 0.5 meters. Okay, could you please calculate this?
.6 times 10 to the power 5.
Wait, okay, what number? 2.6
to the power 5.
10 to the power
5.
5. Microsievert per hour. Now let's see, they give us in sievert. Okay, now we say 2.6 into power. We have here 2.6, this one. Sievert per hour. Let's convert to sievert per hour. Okay, if this is sievert per hour, this will be 0.26 sievert per hour. Okay, let's see what we have here. It is, yes, now, this is in millisievert now, in millisievert. This is in millisievert, 260 millisievert per hour. This is number B. Number B. This is my way to calculate. If you need to use 1.32 as it is, convert this 1.85 10 to the power 5 megabecquerel to be curie. Okay, let's do it here also how to convert one. We'll convert on that. We'll not continue. 1.85 10 to the power 5 megabecquerel. I will move mega. Move. It is 10 to the power 6 mega 10. Now it is becquerel. I need to move in curie. Multiplied by 1 over 3.7 into power 10. Now it is Q. It is good. Did you see now? Okay, I will now this 11. This is 11. 5 plus 6 is 11. Completely, I will have only one here, which is 18.5 divided 3.7. This is, I think, 5. 5. This is 5 curie. So I will put here 1.32 times 5 divided by 0.5. But Röntgen per hour, which is rem per hour. So this amount is 5 curie. Now number 30. Number 30. An americium beryllium neutron source with activity 5 curie emits 4.5 10 to the power 7 neutron per second. Then the equivalent dose rate at a distance 25 centimeters from the source in millisievert per hour, he asked it, in millisievert per hour will be about Now, this is americium beryllium, neutron source. Now, I know here activity 5 curie. This number 5 curie, for me now, I need this number. I need this number 5 curie. I don't need it. For neutron source, I need only number of neutrons emitted. I am not asking about what is the activity of americium. This 5 curie is the activity of the alpha source, americium. I don't need it. I need how many neutrons emit, not what is the decay of americium. Because when americium emit alpha, not all alpha will interact and give neutron at all. So now I need not activity of the americium. I need what is the number of neutron emitted from the source per second. I need this number 4.5 10 to power 7. This 5 curie is etc. information. I don't need it. Take care about the neutrons. You need number of neutron per second, not the activity of the americium. So I have now neutron per second, N. And I know the distance, 25 centimeter, must be in meter. Now, this is americium beryllium. You will find in the data sheet the conversion factor for, we're saying, for energy, and saying 4. Americium beryllium give you number 1.4, 5, 10 to minus 4. This is the number for americium beryllium neutron source. You will find in the data sheet. So now you have C. Because this is americium beryllium, you know the source. From the table you will find C for this americium. Then you have the neutron density. You have the distance, but must be in meter. Then multiplied by 0.08, you get in microsievert per hour. Take care, in microsievert per hour. He need only in millisievert. Okay, when you have this value in micro, divided by 1000. Divided by 1000, you get in millisievert per hour. Let's solve here. So, this rate from neutron 0.08 times conversion factor from the table in data sheet you will find 1.45 10 to minus 4. Now, times what is the neutron intensity? It is 4.5 10 to power 7 neutron per second. Distance is what is the distance? Distance 25 centimeters. So it is 0.25 centimeter square. Now this is the dose rate in microsievert per hour. Okay, can you calculate it please?
Yes, 8,000.
Okay, give me number one by one. 8,
3,
3,
5,
5,
2.
2. Microsievert per hour. Now, in milli divided by 1000. It is 8.352 millisievert per hour. Which is 8.35. Yes, this is number 1, A. This is A. Okay. Number 31. Okay. We'll take this and finish. The dose rate in millisievert per hour. He asked it in millisievert per hour. arising from a thin beta source with activity give you activity. 2 QE, emitting beta particle with maximum energy giving interior electron volt at 0.4 meter distance from the source, taking into consideration that 20% of the energy is absorbed in the source and the air. The dose rate now is about, we know that it's equal 5 times activity in megabecquerel times average energy in millielectron volt divided d square in meter. Now, let's see. Now we have 2 QE. Must convert it to megabecquerel. Must. So it is 2 times 3.7 10 to the power 4. This is now become megabecquerel. Emitting with the energy maximum 316 kilo. This must be in mega. So this is now mega is million, meaning 0.316 million. 0.316 million. But this is maximum. You must divide it by 3. Calculate now normal. Microsiever per hour. Let's calculate it. So now, dose rate from beta equal 5. What is the activity? Mention here 2 QE. This must be in megabecquerel. In megabecquerel, it is 3.7 10 to the power 4. Directly to be in megabecquerel. Times 0.3. What is the energy here? 0.316. Point mega. This is kilo. 16 divided by 3. Which is maximum. I need the average divided by 3. Now, what is the distance? Distance is Bismillah ar-Rahman ar-Rahim. 0.4 meter. 0.4 meter. 0.4 square. Now, could you please calculate this?
Yes, 2 4
2 4
3 5
3 5
8 3
8
8 3.
3 microsiever per hour. Must be in this unit, and this is microsiever per hour. Now, he said 20% absorbed in air, meaning 80% 0.8 absorbed in the body. So I will multiply this now by 0.8. 20% out. 0.8. Multiply this, please, in 0.8.
Yes, 1 9
9
4 8
4 8
6 6.
6 6. This is now in microsiever per hour. Now we need in millisiever per hour. Now 1 2 3. I will now say 194.8. 194 with the none of the above. None. It must be 194 or 195. We don't have here this number. If you see, he give you B. Did you see B? B, the option B. 244 that we calculated here. We calculated here. If you put in milli, this will be 24 and put here point in milli. And you will say 244 milli. Give you this number. Now, if you forget to multiply it by 0.8, you will will say, okay, number B. So in sometimes in exam, he is expect that you will make this mistake. So give you this answer. So it is not none of the above. None of the above. If assume if he didn't say, considering that 20%, if he didn't say this word, it will be 244. It will be 244. If there is no consider 20% energy in the air. Okay, now let's take a break. Inshallah, return at 1:30 to continue with the rest of the course. This calculation, internal calculation and shielding, inshallah. Internal calculations and shielding. So 1:30, inshallah, return back. Source, one theory. And how we select this gamma, you have table according to the unit. You select, you find what is the relation between these two constants in different way, traditional or SI, if you multiply SI by 3.7, you get the traditional. So traditional always greater than SI, greater. So you must multiply SI unit in 3.7 to get the traditional. How to calculate gamma itself? We have information, or we have a relation 0.142 times the energy in fraction, and you make summation for the energy in million electron volt, you will get this value. Now for the beta, we need to calculate according to a certain also relationship. 5 times activity times average energy divided distance squared. Now, activity must be in megabecquerel. Energy must be in MEF, average, MEF, million electron volt. In case if you have E maximum, average equal E maximum over 3. Finished from beta, now neutron. We have another expression also. We have 0.08 times conversion factor times the neutron intensity, not neutron source activity. There is no activity here. It's neutron density or intensity or flux, whatever. Number of neutron per second over distance squared. From where you get this constant conversion factor? From the table according to the energy. For alpha, we say we don't need because it does not represent an external hazard. Now let's speak about internal dose calculations. Now, for dose limit 20 millisievert per year, annual dose limit 20 millisievert per year. This is the total dose 20 millisievert. What is the meaning of total dose? If you're working with a beta, with neutron, with gamma, the total dose from these sources must be not greater than 20. This is a limit. Also, assume I work and I get internal dose. I eat some contamination, some contaminated food, drink, breathe, some air, which contaminated. Now I get dose now internal, committed. Remember this word, committed dose, meaning internal. I get intake, it's called intake. Now, if I get intake or committed dose, I get a dose now. Now, the limit is total external and internal 20. So the total dose, whatever, internal, external, internal alone or external alone, whatever, they are, assume I take only from external, 20. I take only from internal, there is no external, 20. I take from external and 20, and external and internal, 20. So the total is 20. Total is 20, from internal and external. I don't have external, okay, 20. internal. I don't have internal. Okay, 20. I have internal extension 20. So total is 20. Whatever. For example, radiography, they don't have internal. Nuclear gauges, they don't have internal. Okay, 20. Don't say, okay, 20 is divided by internal and extension 10 by 10 and 10. No. No. Total 20. Okay, now, for intake now, I get radioactive material inside our body. Remember this T half effective. Now, this is the internal. Remember this, biological and physical, the amount of radioactive material decreased in our body through biological process and physical process, meaning the decay of the radioactive source. Now, this is the internal. Okay. Internal, I told you, we can say intake. I get intake. The calculation here is very simple calculation. There are tables have a value called ALI. A-L-I. Really it is A-L-I, but we say ALI. A-L-I. This is abbreviation of annual, again, this is annual. Annual limit of intake. This is the ALI, A-L-I, annual limit of intake. What does this mean? Okay, they have table. This table contains this value. Let's explain in the board. They have table like this. Now, first of all, how radiation or radioactive material can enter to our body? Through three ways. Maybe through breathing. Inhalation. This is inhalation. Or maybe through ingestion. Ingestion meaning eating or drinking. Eat or drink. Now, through ingestion. Eating or drinking. Okay. This is the second one. So, first one, breathing, inhalation, and the second, ingestion, eating or drinking, and the third, through absorption. Absorption meaning a person, for example, has a wound, injury, and radioactive material enter to the body through this injury. So it goes through the blood and move and makes circulation in the body. The most important way is inhalation and ingestion. Absorption, forget it. One table like this, say, if it is inhalation, breathing, and another table for ingestion, eating or drinking. This table contains the following. What type of isotope? Isotope. I will say, let's say something like this, copper 60, cesium 137, iridium 192, uranium, and so on. So now, the type of isotope. Now, age from 0 to 1 year, age from 1 year to 5 years, from whatever up, now 18 years and up, adult. We speak now about adult. We are adults. Now we will take this number. Okay, but we have numbers here. Okay, now, in this table, you will find the number here. What is this? Also, the same thing here, huh? Same thing here. I stop, ages, and cobalt, cesium. So you have the same as element you will find here. But this is inhalation, this is engagement. Now, we will find, let's take a number like this. Assume now, for cesium, huh? Let's take for cesium. I found this value. I found 10 to the power 7. What is this 10 to the power 7? This is becquerel. This is becquerel. The values here are activity in becquerel. What is this value of activity? Meaning what? This is annual limit of intake. For cesium here, we have value like this, 5, 10 to the power 6. Becquerel. This is also Ali. But this is for ingestion, eating, drinking. This is for inhalation. So take care about how radiation, how I stop, enter. Through inhalation or through ingestion. Why? For inhalation, I have this value for cesium. If through mouth, eating, drinking, this value. So I have different value according to the way of entering this intake. Now, the physical meaning of this Ali. If this person, through inhalation, I speak now through inhalation, breathe this amount of activity in air contaminated now. Now assume an accident happened, Chernobyl. Now radioactive material in the atmosphere. I breathe now cesium, 137. Breathing. If I breathe this amount 10 to the power 7 becquerel, we call this Ali. 10 to the power 7 becquerel. I breathe one Ali, meaning this amount. This is Ali, one, this amount. If I breathe it, I will get 20 millisievert committed effective dose. So if a person absorb, inhale, breathe this amount and get inside, this amount of activity will lead to decay. This decay meaning absorb energy inside my body. The amount of dose as absorption, this radioisotope cesium, if this amount of decay happen inside my body, this meaning that I receive 20 millisievert. So one Ali, what is that? One Ali, this amount in becquerel. Meaning I will get this committed dose. If now through addition, if I give this 5, 10 to the power 6 becquerel, what is this? This is one Ali from cesium through ingestion. If I get this amount, but by this way, I will get 20 millisievert as a committed dose. Now, as you see, if I get through inhalation this amount, I will receive 20 millisievert. If I take this amount through ingestion, I will get also 20 millisievert. This is Ali inhalation, this is Ali ingestion. Which is more dangerous now? If I get this cesium through inhalation or through ingestion? Cesium is more dangerous through inhalation or through ingestion?
Ingestion is more dangerous, doctor.
Through?
Ingestion.
Yes, through ingestion. Why? I take this amount, this amount is half of this. this amount is half of this. If I say 5, 10 to power 6 divided 10 to power 7, this is meaning 10 times 10 to power 6. This with this meaning half. If I take this amount less than this is half of this. So if I get this amount, I get 20. Meaning cesium through ingestion is more dangerous. Little amount, I will get this. Double of this, but inhalation, I will get 20. So through ingestion, it is worse. Now, let's take an example now. Let's take an example.
دكتور السلام عليكم.
Yes.
أكثر بالنسبة للانجكشن والانهيليشن هل الآن خلينا نقول البيولوجيكال ريسك associated with the whale or with the dog؟ يعني still I have some confusion here about يعني the decision will be made based on the way of route entry to the body or based on the dog race. Based on what we have to decide which one is hazardous than other. Based on what?
Okay. Assume this person now. Assume this breathe cesium. This breathe, assume breathe inhalation cesium 137. And this eat contaminated food. Eat contaminated food also cesium. So this breeze from air, now this is an accident now. This eat, or drink water, contaminated with cesium. But this will not eat, not drink, only breathe. Now, if this breathe, 1, 2, 3, 4, 5, 6, 7. This is 10 to the power 7. Becquerel. And now inside his body this amount. He will receive 20 millisievert. This is called Ali. 10 to the power 7. This is Ali. Amount of activity. For this, if he takes Ali before drinking or eating, only he need 5. 1, 2, 3. 1, 2, 3. Becquerel, he will receive 20. The amount of activity lead to 20. If he eat it or drink it is less than this, meaning this is more dangerous. This amount to give you 20. So this is now through, if I get cesium inside my body through ingestion, eating, drinking, only this amount give me 20. But if it is inhalation, this amount give me 20. So it's dangerous, more in this situation like this. If I receive here the same quantity, here this same quantity by inhalation, only I will receive 10 millisievert. If I receive the same 10 millisievert only, well, this is half of this. So now, slow inhalation is less dangerous than ingestion.
Because the cesium, because it's part of the alpha type.
No, don't think now in alpha or beta or in gamma. Don't think now it enter. We speak now about isotope. You will find, for example, here. You will find here uranium. This is alpha. They give you number here. Take this number only. They make this calculation and they give us table. They give us table here. This amount of activity, whatever, alpha, beta, gamma, electron capture, whatever, this value of activity, after long calculation, complicated calculation, gives me finally a number. If a person breathe please, this amount, he will get 20 millisievert. This is for uranium. This is alpha. I am not thinking about alpha, about gamma. What is the radioactive isotope? This. What is the alley? This. Now, cooler. What is the alley? This. I don't think about this is beta, then gamma. No, at all. Take this number as it is now. Internal is easier than external. This alley is the amount of activity of certain isotope that give you 20. Simple. Okay?
Okay.
So, for example, I will explain now. Assume now a person, an example like this, a person receive intake of cobalt 60. Assume cobalt 60. Intake. Cobalt 60. Asking what is the committed effective dose? Committed effective dose from this intake. He received intake, assume 10 to the power 6 becquerel. This is the amount of activity entered inside the body from cobalt 60. It will lead to committed effective dose. Committed meaning internal. Now, what is the dose come from this intake? He will mention in the exam, alley of cobalt of this intake is, let's say, 10 to the power 7 becquerel. So the question is, one person get intake from cobalt 60. How much? This amount of becquerel. What is the committed effective dose? Result from this intake. Between brackets, alley for this intake is 10 to the power 7 becquerel. As you see, what is the unit of intake? Becquerel. Of activity, becquerel. The problem is so easy. Now I will tell you how. You will write this way. You will write 10 to the power 7 becquerel. This is alley. Amount of activity give you annual limit of intake. We call this amount alley. We know alley gives us.
هل هذا ثابت يا دكتور؟ خلاص اوكي وضحت الان بالنسبه لي.
This is constant. Integral. This is constant. Okay, now it is alley will lead to result in 20 millisievert. This amount we can move and put alley, or put alley and okay. Now we will say 10 to the power 7, which is one alley, give you 20 millisievert per hour. Okay, 20 millisievert as a committed dose. Now I didn't take this amount, which is I take only this. This is the intake. Okay, I will write here. Now, 10 to the power 6 becquerel. Give me how much committed dose? Cross multiplication. This is committed effective dose from this intake.
2 millisievert.
It will be, now I will say, this is committed effective dose equal. This times this, 20 times 10 to the power 6, divided 10 to the power 7. Now, this 7, this all with this, and with this 0. So it is 2 millisievert. So if he take this amount, he will get 2 millisievert. I think it's simple now. Only what you need to put is, put alley here, which is activity given for you, given, not calculated. This is given. Now you will say give you 20 millisievert. How much I get intake? Let's say I take 10 to power. Okay. I will put the intake here. This is the intake. This is the intake. How much committed effective use? Always you multiply this by this divided by this amount that you have. Simple way. Let's take if a person received over 60, what is the amount of intake? Intake always in becquerel. Take care. The intake unit is becquerel. Maybe an exam say the intake unit is, and they give you sievert, rim, becquerel, microscope per hour. Intake becquerel. How many becquerel I get inside? A person intake over 60, 10 to power 7. For example, and I give you numbers. It's random. It's random. I don't know exactly what is the value of cobalt. I need to go to that table, but I give you number only for calculation. This is the amount of intake. And Ali, for cobalt, I give a random. I don't remember the one. Assume Ali of cobalt, assume equal 10 to power, assume something 8. And he get intake for cesium. How much? He get, for example, 5, 10 to power 5 becquerel. Assume Ali of cesium, let's say 5, 10 to power 8 becquerel. This is also becquerel. What does this mean? If he received this amount, he will get 20 millisievert. What does this mean? If he received 10 to power 8 from this cobalt, he will get 20 millisievert. As you see different, depending on the stop. This is from table. I ask you, what is the total committed effective dose? Committed meaning internal. You will say, okay, from cobalt, I will say, I know Ali, which is 10 to power 8. Give me 20 millisievert. He received how much? Only 10 to power 7. becquerel. How much committed effective dose? I don't know. Multiply this by this, divided by this. So committed effective dose equal 20 times 10 to power 7 divided 10 to power 8, which is 2 millisievert. This is for cobalt. Now again, we will do the same thing for cesium. We will say for cesium, 5, 10 to power 8 will give 20 millisievert. But he received, let's say this is 7. This is to be easy because it's a big fraction. Okay, but he received 5, 10 to power 7. How much committed effective dose? This multiply this, divided this. Okay, 5, 10 to power 7 times 20, it will be 10 to power 9. 10 to power 9. Divided. Okay, let's write here to be easy. From cesium, committed effective dose, it is 20 times 5, 10 to power 7, divided 8 to power 5, I think it is 5, for cesium, 5, 10 to 12, this is Ali. So now, 5 with 5. Now, this is 2 millisievert again. So total committed effective dose, this is what? This is total. come from cobalt, come from cesium. It is 2 from cobalt and 2 from cesium. It is 4 millisievert. This is the way. This is the way. Okay, for internal calculation, situation is so simple. Only put the value of I and 20. And what is the intake? Cross multiplication. Now, if a person receives 0.2 Ali, 0.2 Ali, 0.2 Ali, what is the committed effective dose? Same situation, I will say Ali give us 20 millisievert. Now I receive only 0.2 Ali. How much? 0.2 times 20 divided 1. So it is 0.2 times 20, which is 4 millisievert. From the name itself, 0.2 times 20, this is 20. 0.2 times 20, it is 4 millisievert. Half Ali, 10 millisievert. 2 Alis, 2 Ali, 40 millisievert. 3 Alis, 3 times 20, 60 millisievert. So this Ali is 20 millisievert. If you need to put 20 millisievert, is right. If you need to put the becquerel, what is the amount of activity as Ali, multiplied by this, this is now the amount of doses that we receive. This is the internal calculation by simple way. Ali is for ingestion or inhalation. I say, okay, a person inhale or breathe, amount of activity 10 to the power 6 from cobalt. Ali is, and they give you Ali. What is the committed dose limit? Or I can say a person engage, not inhale, eat, drink, food, water. Now ingestion, now not inhalation, ingestion. Now ingestion, I say cobalt 60, ingestion, for example, this amount. What is the committed? So Ali is general for any way of intake, ingestion or inhalation. Now we have another term also very simple. We can express in internal dose calculation. This is called derived air concentration. That derived air concentration. This is a limit also. Remember, what is the annual dose limit? Principal dose limit is what? 20 millisievert, 20 millisievert per year. This is a principle. Remember, our limit is, the hour limit is 10 microsievert per hour. Remember this? Also we have this that. Like hour per hour. But like the hour limit. What is the meaning of this data? Derived air concentration. Okay. Now assume I am staying to explain only. I assume I am staying working in this environment. This is the environmental I am working in it. I am working in this environment. This is the air. From the name itself is air. Derived air concentration. Now, this now, assume now I am in air. Now, this is the environment. I am working in power plant, nuclear power plant. I am working in factory, making radioactive material. This radioactive is gas. This radioactive is gas like iodine, like whatever. And now this radioactive material some or tracer or impurities exist in the air. Now I'm standing in this environment, breathing now. I cannot stop eating. I cannot stop drinking, but cannot stop breathing. Now, assume I'm walking now. When I breathe during this walk, I will breathe radioactive material. So radioactive come inside my body through the air, breathing contaminated air. Now, I will ask you very simple question. What is the maximum concentration of radioactive material in this air? Maximum concentration meaning becquerel per cubic meter of air. Maximum concentration of activity becquerel in cubic meter of air. Each cubic meter of air. What is the maximum concentration of activity in air? And this concentration, when I breathe, I will get at the end of the year, I will get 20 millisievert. Again, when I stand here, I breathe air. Of course, there are concentration of radioactive material here. Maybe the concentration is low, maybe high, maybe medium, different concentration. Now, I will ask about a certain value of concentration. What is this value? What is the concentration here? If I am working 2,000 hours, working normally, I will breathe amount of air during this year. Okay. Now, what is the concentration that will give me at the end of the year 20 millisievert? This concentration is called the derived air concentration. This concentration is the concentration of radioactive material in the unit of becquerel per cubic meter that lead to get at the end of the year 20 millisievert. We call this DAC. For example, if assume for cobalt through inhalation, this is air inhalation. Assume this is 100 becquerel per cubic meter of air. This is the value of DAC. This is the DAC value, 100 becquerel cubic meter for cobalt 60. What does this mean? The meaning that if you are worked normally, the air, this air that I breathe, must not contain more than 100 becquerel per each cubic meter of air at all. Why not more than 100? Because this 100, if you breathe during your work normally, at the end you will get exactly 20. So if you increase this concentration, you will get more than 20. So this is the maximum concentration of cobalt 60 in air. That if I stay working 2,000 hours here, at the end I will get exactly the limit, 20 millisievert. So don't increase the concentration here more than 1 DAC. This is called 1 DAC. DAC of cobalt 60 is 100 becquerel per cubic meter. This also is a constant given for you. Constant. Let's take cesium, another element. The DAC of cesium, I give you number 150 becquerel per cubic meter of air. What does this mean? This means the following. Don't work normally in radiation field has contamination in air greater than 150 becquerel in cubic meter from cesium 137. Why? Because if you work in greater than this value, you will get greater than this. If you work exactly 150 becquerel per cubic meter, you will get committed dose to 20 millisieverts. Can I work less? Yes, of course. It's good. Don't be lower than 20. So this is the concentration that gives you 20. Maximum concentration you can work normally. I say normally. Now the question is, the question is, assume I working in concentration, 3 DAC. Concentration is greater than the maximum 3 times. This DAC is the maximum concentration I can work normally. But the concentration is greater than this by 3 times. 3 DAC. Can I work? Yes, you can work. You can work. How? I will say the following. I will say this is greater than the DAC. How many times? 3. Reduce your time by 3. Instead of working 2,000 hours, working 2,000 divided 3. This is 10 DAC. More concentration. Can I work? This is 10 DAC. Yes. The limit is DAC. Maximum is DAC. 1 DAC. You are working in 10 DAC. Okay, reduce your time by 10 times. 10 times. I'm working 5 DAC. Okay, work. But reduce your time by 5. This is the way. Like, remember, 10 microsieverts per hour. Can I work normally? No. Can I work generally? Yes. Reduce by same amount of increase in 10. So this is the same. Now, the question came in exam like this. Assume a person work in radiation level, concentration equal, assume 20 DAC. 20 DAC. And he working, assume 50 hours. See, he worked for 50 hours in a concentration greater than the limit 20 times. How many? 50 hours. I need now to calculate what is the committed effective dose. The dose that he received. The dose that he received. Now, we will do the following. We will do the following. I know, if I work in 1 DAC for 2,000 hours, 1 DAC, 2,000 hours, what will be the committed dose? 20 millisieverts. Again, this is exactly the concentration, 1 DAC. 1 DAC. Give me, if I work 2,000 hours, I will get at the end of the year 20 millisieverts. This can be written by this way. 1 times 2,000 is 2,000. 2,000. Now, that hour give us 20 millisieverts. 2,000 that hour give us 20 millisieverts. Now, I will do the same thing. Multiply that by the hour. 20 times 50. 20 times 50. I will multiply that, how many that, by the hour. Like this situation. So I will write now 20 times 50. I will write that hours. Give me how much? Cross multiplication. Same like L. I will say this is 1,000. This is 1,000 times 20 divided 2,000. Now I will write again. Committed this one. Committed effective dose. Committed effective dose. This is 20 times 50, 1,000 times 20 divided 2,000. 2,000. Now, 1, 2, 3, 1, 2, 3. 2 with 2, 10. It is 10 millisieverts. This is the way we calculate. Simple. Only multiply in exact. They give you this data. How many data? How many hours? Multiply them by 0. Multiply. Always multiply. Now you have how many data hours? You know that 2,000 data hour, 20 millisieverts. Now, another. If a person work in concentration, let's say 15 days. Can he work normally? Of course, no, at all. He can only work normally 1 day. Only 1 day, normally, 2,000 hours. Why? 2,000 times 1, 2,000 times 1, 2,000. That hour give you 20 millisieverts. Can I work in 50? Yes. Now, reduce the time by 5 times. By 50 times, by 50 times, 50, this is 50, 50 times. Now, he say he work only, yes.
Excuse me.
Huh?
I think you have a problem in the network at your side. Your voice is not clear.
Okay. It's clear now? It's clear now?
No, I think the problem in the network because it's not strong at your side.
Okay, I will see if some open something. This is a optical fiber. This is a, okay, I will see.
اخوي سعد اتوقع مشكله من عندك، انا من عندي واضح، الصوت واضح من عندي.
وانا نفس الشيء الصوت واضح.
يعني عندك واضح؟
مشكله ما عندي
الصوت واضح عندي برضه.
طيب اوكي.
طيب اجل شكله عندي انا. طيب شكرا يا شباب شكرا.
I now make a check for the speed. It's high speed.
الصوت واضح يا دكتور.
الصوت واضح من هنا برضه.
Okay. Now 50 that and work for let's say for 200 hours. Now what is that? Committed effective dose. As I told you, usually always 2,000 that hours lead to 20 millisieverts. This is our reference. Now, how many that hours we have here? 50 times 200 give us 3,1,0,0,0. Okay? That hour committed effective dose. Now, let's multiply 20 cross multiplication to 10,000 divided 2,000. Now 1, 2, 3, 1, 2, 3. This with this 10. 10 times 10, 100 millisieverts. As calculation only, we get it. We get it. Calculation, huh? Calculation. But can he work? Of course, no. Of course, no. Why? 100 millisieverts. For calculation, we say, no, cannot work in this concentration 200 hours at all. At all. How many hours? You will say, okay, now how many hours? This is 50. Greater than the DAC, how many times? 50 times. You must work in only one DAC. But you work in 50 DAC. You will say, time now. 2,000 hours divided 50. Only work for, this is now 80. 80 hours only, he can work. 80 hours only. Why? Greater than the DAC, how much? 50. If a person work only 1 hour, 1 hour in one DAC, 1 hour in one DAC, 1 hour in one DAC, meaning one DAC hour, work only 1 hour, 1 hour, 10 microsievert. If you work 1 hour in one DAC, 10 microsievert. We know that this is the limit, 10 microsievert. So 1 hour working in one DAC, you will receive 10 microsievert, exactly the limit, like this. This is the limit for concentration. For 1 hour, must be not greater than 10 microsievert per hour. This is how we calculate that. How we calculate that.
Can you just repeat? Can you just repeat the last?
This one.
result you have made?
This one.
Yeah, because I mean, I'm good in terms of calculation but the decision.
Okay. If a person work 1 hour, 1 hour.
Why? Just give me a minute, because why we say this person he's not able to work with this
This one.
tech. Yeah, the last step just.
Okay. Person work in 50 DAC. And he work, let's say, 200 hours. Make only calculation. The calculation is easy, huh? Calculation. Repeat or?
Yeah, it's clear, the calculation. We didn't have an issue with the calculation.
So he received during 2,000 hours in this concentration, as you see, 100 millisieverts. Cannot work in this by this time at all. At all. Why? At the end of the year, he will receive 100 millisieverts. The limit is 20. So you cannot work. Not accepted. Now, if I told you, how can I manage this worker to work in 50 DAC? What is the maximum time he can stay? 2 hours, 200 hours? Of course, no, because it will give 100. How many hours? I will tell you. Okay. Now, I will say, he must not exceed than 1 DAC. 1 DAC. Normal. 1 DAC normal. But he work in 50. Greater. How many greater than 1 DAC? You are greater than the normal by 50 times. This number. You are greater than the normal by 50 times. Now, decrease your time 50 times. You are working 2,000 hours. Normally. Now, decrease 50 times. You only need to work in 1 DAC, but you work in 50. Greater than the DAC by 50 times. So divide this total number of hours per year by 50. So this is how much? 0 is 0, 5, with this 4, and you have 0 here, it's 40, right? 40 hours. He must work 40 hours, no more than this. No more than this. Only. If a person work only 1 hour, only 1 hour. In concentration 1 DAC. He used 1 hour, 1 DAC, 10 microsievert per hour. 10 microsievert per hour. So if he's staying 2,000 hours, he will get 20. Remember this limit? This limit per hour also must not exceed in an hour. And do not exceed in this concentration also 1 DAC. 1 DAC, 1 hour, 10 microsievert per hour. Okay. Let's see the slides. You see the examples here. Annual limit of intake. Unit is becquerel always. The intake of a given nucleides in becquerel in a year by a reference man, which results in a committed dose equal to the relevant annual dose limit 20 millisievert. Ali for cobalt ingestion, for example, is this amount. This amount. If a person takes through ingestion, eating, drinking, this amount will lead to 20 millisievert. For inhalation, for the same, but inhalation, now another value. This is 10 to the power 6. This is 10 to the power 5. This is 10 to the power 6, and this is 10 to the power 5. This means what? This means that if we receive less amount through inhalation, will lead to 20. So inhalation for cobalt is more dangerous than ingestion, as we said before. Now, air concentration, derived air concentration. This is the maximum concentration, becquerel per cubic meter, of a single nuclei in air at the working place for an occupational reference man breathing, for which during the whole working hour will get, for 2,000 hours, believe, he will get 20 millisievert. 20 millisievert. Now, if we take an example, a worker was exposed internally to 0.4 Ali. Ali is 20. 0.4 of 20, okay. And inhaled, get inhaled 100, 1,000 DAC hour. So the external dose should not be exceed in that year, okay. Now, this Ali and the inhaled DAC per hour is internal. He get a dose from this internal, two internal. Ali and inhalation. Now, this person get a dose from internal. Let's say, I will now solve, but let's say, he received, assume 15 from internal. Now, he allow only to take 5, only 5 from external. Why 5? Because the total is 20 limit. And he gets 15 from internal. So the rest is 5 from external. So he cannot take from external more than 5. This is what he's asking about. So let's solve it now. I say Ali is 20 millisievert. 0.4 Ali is what? 0.4 times 20. 8 millisievert. Now for inhalation, I know that 2,000 DAC hour, this is reference for us. 2,000 DAC hour, 20 millisievert. 2,000 DAC hour, 20 millisievert. Now 1,000 DAC hour, because I multiplied now, let's say 1,000 DAC hour. I forget only to put here hour. To put here also hour. 1,000, hey, above. 1,000 DAC hour. Give you how much? Cross multiplication. So it will give 10 millisievert. Now we take 8 millisievert from Ali and get from inhalation this amount. 8 plus 10, 18. So we take internally 18 millisievert. The rest is 2. The rest is 2 millisievert. Another example. A worker get intake 10 to the power 5 becquerel. 8 to 10 to the power 5 becquerel of a radioactive isotope. The annual limit of its intake, Ali, is 1.6 10 to the power 6. Give you now Ali. And also he inhaled 400 DAC hour. So its total dose, committed dose in this year is how much dose he received. Okay, I will say Ali, which is 1.6 10 to the power 6, this is Ali, is 20 millisievert. Now, he received how much? 8 10 to the power 5. Now, cross multiplication again. 8 10 to the power 5 times 20 divided this amount of Ali. So he received 10 millisievert. How many hours DAC? He say 400 DAC hour. I know that 2000 DAC hour, 20 millisievert. So 400. Alhamdulillah. So 400 DAC hour, how much? Cross multiplication again. 4 millisievert. Now, he take 4 inhalation, 10 from Ali, 10 plus 4, 14 millisievert. This is the total internal dose, committed dose. If I ask, how much external can he expose during this year? Only 6. Because the total 20. He received the internal 14. The rest as an external 6 only. 6 millisievert.
Doctor?
Yes.
In terms of external dose, that means it should include both Ali and DAC, huh?
Yes, of course. Internal, if we take, for example, Ali from Cuba, inhaled 8 contaminated from Cuba, inhaled contaminated with cesium, breathe or drink from America, you must collect each one and make a submission. This is internal now.
Also, the total dose is also meaning the external dose. Both of them are equal to each other, right?
I can't tell you again.
The total dose also
20.
meaning the I mean in terms of abbreviation, the total dose equal to the external dose. I mean in terms of the abbreviation, the question. الاثنين كلهم زي بعض، يعني هو في الاخير بيطلب العلي والداك.
هو هنا في المساله دي ما طلبش غير هنا في المساله دي في المساله دي طلب بس قال لي the total dose received in this year. فهي 14 يعني هو اخذ 14 داخلي من الانتاج ده ومن الداك ده اخذ 14. ده اللي سأله.
التوتال هنا يقصد فيها العلي او الداك؟
لا ما هو اخذ ما هو بلع ماده مشعه اخذ منها 10 وبعدين اتنفس ماده مشعه اخذ منها 4. فالداخلي كله كام دلوقتي؟ الداخلي كله كام؟ 10 و4. بلع اكل ملوث اخذ منه 10 اللي هو اعطاهوني ده اللي هو علي ده. وتنفس هواء ملوث قدره 400 داك ساعه. يعني كل قعد مثلا 400 ساعه يتنفس هواء والتركيز بتاعه 1 داك، او قعد 200 ساعه والتركيز بتاعه 2 داك. في الاخر خالص اخذ تنفس 400 داك ساعه. فهو اكل تلوث، ده دوز لوحدها. تنفس تلوث، ده دوز لوحدها. اجمع الاثنين بقى مع بعض.
ايوه انا اقصد التوتال دوز، يعني هي مجموع الاثنين العلي والداك في كل الاحوال. يعني
نعم
واضح ممتاز.
نعم. لو انا طلبت بقى حاجه زياده وقلت طب هو لسه له قد ايه اكسترنال ممكن ياخد؟ هل ياخد 20؟ لا، لانه كان اخذ من الداخلي 14، يبقى ياخد ال 20 ناقص 14. لو هيتعامل مع مصادر خارجيه يبقى ياخد بس 6 خلال هذا العام كله. We finished now from internal. Let's speak about shielding now. Shielding. Okay. As you see in this drawing, we have a source here. We have a source here. Emit radiation. Okay. Assume this is 2 centimeter or 3 centimeter thickness. If I am standing here, the dose, I will receive big amount of dose. So the dose here without shield will be what? I not, dose will be D, this dose. So if there is no shield here, I will receive D dot. So without shield, I will receive D dot. This is the dose I will receive here. If I put now shield now, I will receive another dose. Why? Because this shield will absorb some of these doses. Now, assume there is no shield again. There is no shield. Can I calculate the dose here? Yes, I can. If I know the activity, if I know, now this distance, I know the source. Now this shielding for gamma, take care. This, when we speak now about shield, we're shielding gamma. This is gamma shielding. So now, if I know the activity, I can know the dose here in air. There is no shield. By the equation, dose rate equal gamma constant, time activity divided by square. So I can calculate the dose rate here without shield. Now I put shield now. Now, the dose I can calculate by this way. The dose now is D dot times 0.5 x over x half. We give this information when we speak about gamma, if you remember. So now, what is this x half? This is half value layer. This is the thickness required. To reduce this D dot to become D dot over 2. So x half is the thickness of shielding. Reduce this dose to half. If this is 100, behind shield must be 50. This is half value layer. Depending on what? Depending on this material. Concrete, lead, tungsten, uranium, whatever. And also, at the same time, depends on the source. Remember, x half on the energy and the material type, Z. We say this is in the gamma. This is how to calculate. If you need, for example, I don't need those. Now, I know the source, emit, amount of radiations. This is the amount of radiation. 100 gamma per second. How many gamma per second behind the shield? Okay, the same equation. This is without shield. Now, with shield, I times, I know, half x half. Whatever it is a dose rate, it is a number per second, we will use the same. This is how to calculate the dose. Let's take an example. Assume this is a source, emit radiation. I'm standing here. Now I receive a dose directly. Okay. Here I receive without shield dose. This is D dot. I receive here D dot. Now I will put a shield now. Now I receive less. Why? Because this is the shield will absorb some of this D dot and reach only D. So we have now, what is the dose after thickness X if please, I have here. Okay. The connection is good for you because I get a message here that something happened. Okay. The connection is okay. Connection.
Yes, yes.
Okay.
So much.
Okay. Because I received a message here. Something here. Okay. So the dose after X. This is the thickness X of shield equal. What is the dose without shield? D dot. Multiply by half thickness of the shield over X half. Take an example now. Assume that dose without shield in air. Without shield meaning in air. The dose in without shield is 10 CFR per hour. What is this without shield? Without shield. This means what? D dot. Okay. I need to reduce it so I can walk safely behind the shield. This is the source. Without shield, give me 10 CFR per hour. This, if I stay 1 hour, I will die. I will die if I stay 1 hour here. For example, there are a factory in Dammam using for sterilization for medical equipment, like syringe, like something like this, used for 400,000 cubic. The dose there is high dose. You need to have this 1,000 times. Now, we need to make shielding, so he can work in this area. Now, I ask, what is the shielding minimum thickness he needs? Minimum thickness he needs. So my question is, what is the minimum X he needs from concrete? I will make concrete. Minimum X, I don't know. I need to calculate. The material is concrete. Half value here, X half equal, let's say 4 centimeters. 4 centimeters. Number, it's a number. Now, what is the minimum thickness? I don't know. I don't know X. I know X half. I know the dose without shield, 10. But I don't know this. I need to know all except X. I need to calculate. So I must know X half. I get D dot, I get. But what is this? This is the limit here. At least must be 10 microsievert per hour. Remember the limit? At least 10 microsievert per hour. I can't accept 20 microsievert per hour. I can't accept 15 microsievert. I accept 10 microsievert per hour. This is the maximum I can accept. But this is the limit. If I stay 2,000 hours here, I will get 20 millisievert. Now, this is 10 microsievert per hour. I will write 10 microsievert But I want it to remember only. Equal. What is that? Goes without shield. It is 10. But 10 what? 10 sieve. And here micro. I need to put here micro. Okay. Put micro and divide it by macro. I will now put micro sieve there out. I need to put here over micro, which is 10 to minus 6. Get up, it becomes 10 to the power 6. Now it is micro. 10 times 10 to the power 6, which is 10 to the power 7. Micro sieve بالأول. Now it's micro بالأول. Micro and this micro. Times half. I don't know x. I have x half, 4. I will write now. Remember, I have exponent here now. Remember what we make? We make length. This is 10 over 10 power 7. I will bring this here. I will bring this 10 to the power 7 here. Now length 10 to 10 to the power 7 equal x over 4 length half. Now, can you calculate this, please? Calculate this. Length this is 10 to minus 6. This is 10. This is 10 to minus 6. If we get up, it will be 10 to minus 6. How much is this?
Minus 13.8.
Okay, minus 13.8. Let's say 14, huh? Let's say 14. Let's say 14. Let's say minus equal x 4. And this is minus 0.693. Minus. Minus with minus. Move. Finish. So x is equal x equal 14 times 4 over 0.693. What is this? Can you please give me this number?
80.8.
Number by number. How much?
80.8.
80.8 centimeter. Why centimeter? Because I give x half in centimeter. This must be in centimeter. This is how to calculate. This is how to calculate. Okay. This is the minimum thickness I need. About 81 centimeter. Let's put here. Minimum thickness is 81 centimeter. So, by calculation, if this is the source, I put a thickness 81 centimeter. I calculate this is 10 microsievert per hour. Without this, I will receive 10 sievert per hour. So this is the dose without shield. Just I put 81 centimeter, I reduce to 10. Okay. Until now it's clear. Because I will do now further step. Clear?
Clear.
Okay. Now I will bring the detector to check if this calculation is right or wrong. Now I will make a test. I will bring the detector in this side, directly in this wall. Now let's measure the dose rate. Let's measure the dose rate. I must find the dose rate. What is the dose rate I need, or I must be on the detector? The detector will measure how much? Give me number. To measure, what is the dose rate? The detector will measure
10 microsievert.
10 microsievert. Must measure 10 microsievert. I calculated, 10 microsievert. This is, I expect to measure 10 microsievert. And it must, according to calculation. This is clear now. From calculation, it is 10. When I put a detector here, it must be 10. It must be 10. Now, real situation. If I went to this point and measure on the surface of the shield, I will not find 10. I will not find 10. I will always, not sometimes, always find the measure, not calculated. This is calculated. This is calculated. The measurement is 20, 25, 30, maybe 40, maybe 100, maybe 200 even. Maybe 1,000, 1,000 and a half, maybe. Always I will find the measure when I make a verification for my calculation. Always I will find the measurement greater than calculation. Now, why?
Why?
Background radians.
I will explain. So why always I find measure the greater than calculation. And how to correct my calculation to be as measured. I need now to explain why always measure greater than calculation and how to correct the calculation to be as measured. First thing, let's explain why. Why? This equation when you can use it to calculate I speak now about gamma. I repeat it again. This is shielding for gamma sources only. When I use this equation, I calculate the dose that come from direct radiation. What does this mean? Assume this is the source. Emit radiation. This is gamma. Move. Now inside the shield. Stop. Completely absorbed. Photoelectric. Stop completely. Now another gamma. Move. Now absorbed. Photoelectric. Finished. Another one. Gamma. Now, computon scattering. Remember, computon part of gamma absorbed, and I will have another gamma move in this direction. Change. Now, absorbed photoelectric. Finished. Now, another gamma. Move without any interaction. without any interaction. Another gamma. Move without any interaction. Another gamma. Move, making combinatorial scattering. Now combinatorial scattering. And escape from the shield. This is combinatorial scattering and absorbed after this in photoelectric. But this combinator and appear behind the shield. Assume now gamma. Combinatorial scattering appear behind the shield. Assume another gamma. Make Bayer production. This source, high energy, will take all the possibility now. Make Bayer production. Now, Bayer production, two gas. One here, one the other side. Now, behind the shield, I have now the following. Only this is combinatorial scattering. This is come from combinatorial scattering. Remember this? Make combinatorial scattering and appear here. This is come from Bayer production. This come also from combinatorial scattering. This one, move and scatter. This come directly from the source. This is called primary radiation. Why? Come directly from the source. Direct. Primary. This is primary. Come from the source directly. Now, this again, this one, move. Primary also here. This is also primary. I found behind the shield something come directly from the source, primary. And some come from combinatorial scattering, like this, and some like this, Bayer production. The calculation only calculate dose or radiation from primary. The calculation does not take into account combinatorial scattering and Bayer production. Only calculate the dose come from primary. But if I am standing here, if I am standing in this side, I will get from primary, from combinatorial scattering, from Bayer production. If I put the detector here, detector does not know anything about primary or whatever. You will see all this radiation. So we will measure this, and this, and this, and this, and this. It will measure all of this radiation. So he measure this, and this, and this. More than the calculation. So he measured all, calculation measured only this, primary. So this is why always I found behind the shield from calculation, the calculation is less than real. This is the real. This is the measure. All these are the measure. And only calculated this. This is why we call this phenomena that we find some scattered radiation like Bayer production or combinatorial scattering. We say this shielding may build up of radiation behind the shield. We call this process build up process. We build up, increase the radiation behind the shield because combinatorial and Bayer production. This process inside the shield that leads to this scattering radiation, we call this build up process. So now, as they build up process inside the shield, I get scattered from Bayer production, combinatorial scattering, and this in measurement taken into account. For calculation, no, only take this into account. Calculate this only. This is why calculation always less than measure. Now, in exam, in exam. We will now see how, we now make interpretation, or we now explain. We make interpretation or explanation why always greater than calculated. Now, in exam, before going to how to correct this, in exam now. In exam, if he asks, build up behind the sheet is a result from, and they give you options, from photoelectric and Compton scattering. Compton scattering, Bayer production. Photoelectric and Bayer production. Which one is the correct answer? This build up, this is scattering, as a result of photoelectric, Compton scattering, Bayer production, photoelectric and Bayer production. Of course, this scatter comes only from Compton scattering and Bayer production. Photoelectric completely absorbed the gamma, completely absorbing gamma. There is no scatter from photoelectric. The photon completely absorbed, disappeared inside the shield. So the build-up phenomena behind the shield is a result from Compton scattering and Bayer production. This is came in exam. This is an exam. Usually you find this question. Now, I need your answer for this question. I need your answer. If this is the cesium, now I specify. Generally, this one. Now I will specify. Cesium 137. Cesium 137. Build up behind the shield is a result of what?
Compton scattering only.
I need answer. Is a result of
Electron capture also.
from
Electron capture.
capture
Compton,
from
Compton scattering only.
From Compton scatter. Compton scatter.
cesium. Remember, the energy of cesium is lower than 1.0.
Compton scattering.
Only if build up happened behind the shield, if the build up occurs by the shield, it will be only Compton scattering. There is no Bayer production because the energy of this cesium is lower than 1.022. You must know this now. You must know that this cannot make build up as a result of Bayer production. Because its energy is less than 1.022. So for cesium, only Compton scattering. Generally, if an exam asks them generally, Compton scattering, Bayer production can produce scattered hair photos.
Sir, I have one question.
Can you please raise your voice?
Sir, I have one question. Can you hear me?
Yes, yes.
During photoelectric effect, there is a possibility of generating X-ray. Why you are not taking the X-ray in consideration as a secondary?
Okay. Here, for gamma, photoelectric, some X-ray may appear. This photoelectric, for this low energy, for example, cesium 0.66 MeV, 0.662 MeV, the X-ray is in something like 0.01. This is so high X-ray. Real, it's something like this. MeV. Very, very, very low X-ray. Be sure that Remember, photoelectric probability become high when your energy is low. This will be absorbed X-ray in this material. Very low. Remember, photoelectric proportional to 1/E. This is very low, very low, meaning this is so high. X-ray will be absorbed here. Will not take into account. 4 cobalt energy now 117,133 million electron volt. Here we have possibility to Baire production. 4 cobalt 60. If this is cobalt 60, now build up Compton scattering and Baire production. Cesium only Compton scattering. For X-ray from photoelectric, very low, absorbed in the same place that making photoelectric. Now, the last thing about this session for calculation is, now we know how to make explanation about, we get explanation about why always we find the measure of greater. Because the calculations take into account only primary. The radiation comes directly, does not taking into account the scatter. How to correct this? We will do this. D after X equal. Now I will write the same thing. There is no any problem. Okay, any change now. Half X over X half. The same. Only I will put here a correction factor called B, build up factor. This called build up factor. What is this factor? This is correction factor. This is correction factor. He will give this factor for you. He will say, assume an exam. Assume, we will find problems like this in exam. In the model that we run. He said, we'll ask, we have a problem like this in the model. We have a dose rate without shield, this 10 microsievert, this 10 sievert per hour. And we need to make a shielding. What is the minimum X thickness? Half layer is this value. You will say, okay, this must be 10 microsievert per hour. This is 10, and you give this calculation. You give this number. Remember this number? He will ask this. In the second problem, this number, for example, 30, problem number 31, question number 31. He will say, in case, if you take into account, build up, what will be the minimum thickness? Of course, minimum thickness without build up, and didn't mention anything about build up, this is the minimum thickness. But he will ask again, in case, if you take into account build up, what will be the minimum thickness? You will say, I will use this calculation. I need to put here build up. And he will say, consider build up factor, let's say 20. So now you will use the same equation. He say build up factor is 20, I will write this. This is 10 microsievert per hour equal He say build up 20. I will put right here 20. I will write here 20. Only I will change this. Put 20 here. Multiply it 5. 10 to the power 7 microsievert per hour. Remember this? It was 10 to the power 7 microsievert per hour. 10 sievert per hour is 10 to the power 7 micro, like this, micro. Now, 0.5 x over x half, 4. Only you added this number. If he give to you, if he didn't mention, take it 1. Don't put it 1. Consider it's 1. Consider 1 and calculate. Now, we will say this 10 divided, take all this in this side. This is 2, 10 to the power 8. 0 is this, 8, and this is 2. 2, 10 to the power 8. Now, equal 0.5 x over 4. But I will take ln now. So I will bring this here. X over 4 ln. Now, let's calculate this. Let's calculate this. Give me please this calculation if you wish. Okay, please. This is calculated. Minus okay, if I calculate it, now I will get x. This x, I am sure, greater than 81. Assume about 100 centimeters. To save time only, not waiting for that. So now, I need more thickness. Why? Because there is build up behind sheet. Coming from what? From computer scattering and from bare production. Only you can continue, but if he mentioned build up, put the value in, put only build up in, and continue, Now, what is the meaning, now physical meaning? Assume I say build up equal to 20, as we said here, 20. What does this mean? The meaning is, this is a sheet. The tools without shield, by calculation, is a certain number. Those rate is a certain number. If the shield say build up 20, when you go to measure here, the value of radiation dose rate is 20 times greater calculated. This 20 meaning what? If I calculated 1 microsievert per air, 1 microsievert behind the sheet. Calculate 1 microsievert. Really, it is 20 microsievert. If this is assume, this is 2 microsievert. Calculation, 2 microsievert, calculation. This is 2 times 20, 40 microsievert. This is the amount of increasing than calculated. This is 5 microsievert, 5 calculation, real 100, 5 times 20, 100. Now, do you know exactly what is the meaning of build up? This is a build up. Now, physical meaning only. I can now explain build up from this. Now, how many primary we have? How many primary? Please, I need interaction from you. How many primary we have? How many primary?
2.
Huh?
2.
2. We have 2. I will write here. I will write here. We have 2 primary. From the reason from the source. 2. 2. 2 primary. 2 primary. Total. How many?
5.
5. 1, 2, 3, 4, 5. Total. I calculate only 2. Measure 5. I calculate only 2. Measure 5. Now, build-up factor is total over primary. This is a build-up. Build-up in this shield is 5 over 2. This is the meaning of build-up. 5 over 2. This build-up is experimental value. This is experimental value. This is corrected value. Experimental. This is 5 over 2. This is a build-up. I will approve now. This build-up is 5 over 2. I will approve for you now. This is 5 over 2. Okay. When I calculate, I told you I can say I instead of doing the same. I after x by calculation is 2. Primary. I after x measure is 5. This is calculation. 5. I need this 2 to become 5. I need to correct this to become 5. I will multiply by 5 over 2. This is a build-up. 5 over 2. 5 over 2. Total over primary. Now, if we multiply now, it is 5. Now, calculation as measured. Calculation as measured. So build up, really, build up is what? It is total. Gamma divided by primary gamma. Total gamma is primary plus secondary. Come from scattering. Divided primary. Total divided by, as we said in the total 5 divided primary 2. This 5 is 2 primary, 3 secondary. 5 is primary plus secondary. Scattered. Meaning primary plus secondary divide primary. Assume build up equal 5. Assume 5. I ask you, how many, or what is the fraction of radiation behind the shield? This is the shield. Now radiation sometimes come like this, and sometimes like extraction, like this, like scattering, and some come. Now I ask you, if the build-up factor for this shield is 5, what is the fraction of primary to total, and fraction of secondary to total? It's so easy. Why? This 5, build up 5, meaning what? Write by this way. Write by this way. I need for you to write by this way. Now, this represents the primary. This is the primary. Remember? total divide primary. This is represent the primary. This is the total. This is the total. I will write by this way. This primary 1. Total 5. So remember, secondary is 4. Primary, this is primary and secondary. Primary 1. So this is 4. 1 plus 4 is 5. Divided 1. Now, what you need now, fraction of primary to total, this is a primary. Total 5. So, fraction of primary to total is primary 1, total 5. 1 over 5, meaning 20%. Meaning what? If you have now here total 100 gamma, 100 gamma behind the shield, 120 directly from the radiation, from the source, directly from the source, and 80 for secondary over 5, which is 80%. 80 from scattered. This is the meaning of Bell effect. Total divided primary. Experimental. This is experimental value. So, I will write by this way. 5 over 1. 1 primary, total 5. Okay, 5 primary plus secondary. 1 plus 4, 5. Now, primary 1, secondary 2. Let's take another example. Assume this is a shield. Last example. This is a shield, X. Now, behind the shield, assume total, assume 10 to the power 8 gamma per second. Always 8 to the power gamma per second. Behind the shield, this is the total. Measure. Build up equal, let's say 10. This is the build up. Now I ask how many gamma per second directly from source, and how many gamma per second is scattered inside the shield and appear behind the shield. 10 build up, 10. I will write 10 by this way. By this way. Now, this 10 is 1 plus 9. Over 1. Now, you need what? Fraction. No, number. From this. Directly, okay. I know the fraction is 1 over 10. From each 10, I have 1 primary and the 9 scattered. Each 10 total. I found 1 primary and 9 secondary. So now, 1 over 10. 1 gamma among 10 primary multiplied by this. So it is 10 to the power 7 gamma per second come directly from the source. Now, how many secondary? 9 secondary. Total 10. So each 10 here, I found 9 scattered. So 9 over 10, 5. 10 to the power 8. I will find 9, 10 to the power 7. Gamma per second, secondary, behind the shield. This built up, in this way. Another interpretation for this. If I measure here, measure this amount, if I calculate, this will be less by this 10 times. If I calculated, the calculation will be less than measure 10 times. This is the meaning. Sometimes in radiography, they found some time. They give overexposure in the film, saying we get overexposure. Why? This build-up. Build-up give a lot of X-ray, a lot of gamma ray scatter. The build-up is high. So you calculate or get a certain amount. But the build-up was higher than you expect. You expect, for example, you expect 10 build-up, and it was 12. Now you get more radiation, so your film become overexposure. Or sometimes you get less. You can, for example, you expected 10, and it was 8. So you have now less radiation. So the measurement, the exposure time was less than you need. In case of overexposure, now you calculated build up less than real. So you get more radiation. This is the build up factor calculations. Okay, so now let's now see this. Okay, as you see, this is the shield. In case of you don't build up, in case in exam does mention build up, take it 1. There is no build up, take it 1. Measure the equal calculation. Okay, in case of he give you build up, only you need to put build up here. Put the build up here. Now, as you see in this detector, if I calculate, I will calculate this only, this one. Come directly from the source, this one. This is calculated. But the detector will measure, this is scattered from, this is annihilation radiation. Remember annihilation radiation, gamma to gamma, I will measure this, and this is scattering, computer. So detector will measure 3 gamma, but I will calculate only 1, this one. Now, as I told you, primary photon plus secondary photons, gamma, over primary photons. Now this is the meaning of build up, and I will put here to correct. And this is in case of you asking about the percentage of radiation behind the shield, the primary and secondary, I will write by this way. As I told you, assume this is 5 over 1. 5 is total over primary. Total is primary plus secondary. So it is 1 plus 4. Now, 1 over 5 is primary, coming directly behind the shield. So, we finish now from the calculations of how to calculate shielding. Last thing about this, and I prefer both in the book. 5 minutes to take break. Yes. Alhamdulillah, this is the last one. Let's do it. I need only this. I have material number 1. I have another material number 2. Material number 3. Material number 4. Different material, different material. I need to make a shielding for gamma or even neutron. Gamma or even neutron, Gamma or even neutron. Material for gamma, for example, stainless steel, concrete, lead, and for neutron, let's say, assume polyethylene, wax, whatever. Okay, but different gammas. This concept applies for neutron and for gamma also. Now, assume now I have this number 1, material number 1, material number 2, material number 3, material number 4. Now, half value layer also we have the same concept, half value layer for neutron. For neutron also, because it's probability. Okay, half value layer equal 2 centimeter. Half value layer equal, let's say, 3 centimeter. Half value layer assume equal 4 centimeter. Half value layer assume equal 2.5 centimeter. Different material. Why? This gives you indication it's different material. If the same, for example, 2 and 2, same material. But different x half, different materials. Now, thickness here, the thickness here is assume 10 centimeters. Thickness. Thickness 10 centimeters. Thickness here is, let's say, 12 centimeters. Thickness here is, let's say, let's say 18 centimeters. Thickness here, let's say 16 centimeters. Okay. My question is, which material you will use as shielding? Whatever, for gamma or for neutron. So in exam, if you give something like this for neutron, don't worry. Take the same concept. For gamma, same concept. Now, my question is, which material you will use as shielding material? Give me an idea. Give me an idea. I need idea now. Don't tell me number 1, number 2, number 3. Give me idea now. How you can select?
Should be less, x half should be as low as possible.
Okay. One idea is x half as low as possible. That's a good idea. You have another idea? Okay, the idea is you say x half as low as possible. Yes, this is your criteria, but with a little modification. Now, of course, I know, if I have the same thickness, 10 centimeter, 10 centimeter, 10 centimeter, 10 centimeter, I will choose this. If they are equal in thickness, 10 centimeter, 10 centimeter, 10 centimeter, 10 centimeter, I will use this. 12 centimeter, 12 centimeter, 12 centimeter, 12 centimeter, I will choose this. Of course. Sure. But now different thickness. So now, remember the fraction of remaining. Really, I will select this material. The material that make this high value. X over x half. X over x half. I will not calculate this at all. Only I calculate this. X over x half. But why I want this? To give you an idea. When this increase, the remaining fraction, remaining 2 behind the shield become 1. So now I will say x, which is 10 divided 2. X divided 2. Here, 12 divided 3. Here, 18 divided 3. Here, 16 divided 2.5. This is 6. This is 5. I will cancel this. Because this is 5. This is 4. I will cancel this. This is 6. Now compare this with this. Which is higher? This is give you how much? If I multiply
6.4.
By 4, this is now 10. But this is now 10.
6.4.
Doctor, box number
now,
3. Yeah,
this is 6, this is 6.4. This is that 6.4. This is 6. 18 divided 3, 6.
4, not 3.
16 divided 2.4, 5, it is 6.4. So I will use this material. I will use this material. Why? Because x over x half is 6.4. This will be very low. This is the remaining dose by the shield. Become very low. So in case of you find problem in exam like this, you select, you make what? Dividing x over x half, which give you the higher value, take it. Take it. Because this is 5 value layers, only 5 value layers, 1, 2, 3, 4, 5. Here we have 1, 2, 3, 4, 5, 6 value layers. So I will reduce so much. Here we have 1, 2, 3, 4, 5, 6, and this 0.4. So I have much half value layers. So I will decrease so much. Now let's take a break for break, and inshallah we will continue after break to finish from the regulation. Only not greater than inshallah 30 minutes, inshallah, to finish from the rest of regulation. Okay. Inshallah, see you at 4:15. 4:15 to continue inshallah with regulation. We now we finish from calculation, huh? So now let's write 4:15. Return inshallah back to continue and finish inshallah in our time. Bismillah. Okay, this is the break time.
So, sir, I have one quick question for you.
Okay.
So, is there any thickness for the consideration of build-up factor? Any specific thickness, like?
Can you ask your first, please? Is there what?
Is there any specific thickness so that we can consider the build-up factor?
We can consider what?
For considering build-up factor, is there any specific thickness, like beyond this, the build-up is happened, or?
No. Oh, yes, I will explain. Build-up factor is experimental factor, and depends on the following. Build-up depends on, I will write here, depends, but this is beyond the course, huh? This is not included the course. This build-up is so complicated issue. Now, build-up depends on the following: material, Z, I mean, okay, material, depend on energy, type of source, the energy of source, depends on the thickness of the shielding itself, depends on the thickness itself. If you have the same source, for example, cobalt 60, and you have the same material, lead, and you assume two same activity, same activity, source, cobalt, same material. Now you assume 1 centimeter lead. Build up, assume is 10. If you bring 12 centimeter instead of 10, build up is different. Greater or lower, I don't know, but it's different. It's different for the thickness. Even sometimes on activity. Sometimes for certain specification, for certain configuration, but mainly depends on thickness, depends on material, depends on energy. really, when we make design for shielding in real situation now, I speak about real situation, we make what is called trial and errors. We make trial and error. We now assume shielding without calculate, without build up, and we get number. Now we go to the table. We go to the table, bring the build up for this thickness we expected, because we need to expect thickness first. Let's say without calculate, without build up, let's say 10 centimeters. I will go to the table. This is Cobalt 60. This is the lid. This is the thickness. What is the build up? Assume 5. I will use 5. Now put the 5. I get another thickness. New thickness, higher. Now, take this thickness. Take this thickness. Now, this is the first trial for me now. I will take this calculated, without build up. See what will be the do's behind the shield. Now, I found this is a certain value. Take this again and put in the calculation with build up. I will find it's higher than what I expect. Now increase the thickness. Go to that. It's a trial and error until you reach to some. We can say some the deviation become so close. So now I make some what is called the conversion or the deviation become now close until now I reach to a certain value. When I make the certain trial and error, I will find the error is 0.00001. So stop. This was my thickness. This is my thickness. So for build up, usually for radiography, you used, for example, 1 centimeter, 2 centimeter thickness of stainless steel pipe, 0.5 centimeter. You have some build up, but low amount, about 5 to 3, something like this. If you have more thickness, now you need to take into account, maybe build up reach to 100 even. More thickness, more build up. So you need to take into account. Sometimes we find the radiation dose behind the shield is greater than the calculated, maybe sometimes 100 times, 100,000 times, 100,000 times, sometimes. The build up, in some cases, sometimes give you higher than the calculated, greater than 100,000 times. For low thickness and light material, for example, millimeter. Okay. Do you have a problem in the connection?
Yes, sir. Yes, sir.
I give a message now. I don't know why.
Okay.
Okay. But okay. Did you hear my answer?
Yes, sir. I can hear you now.
Okay. I told you. Usually, for low thickness, 1 meter, 1 millimeter, 2 millimeter of stainless steel, you can neglect build up. For large thickness, 2, 3, 4 centimeter, you cannot neglect.
Okay, sir.
Okay. But I give a long answer. Did you hear it before or not?
Yes, I heard before also.
Okay, that's good.
Again, I lost the connection for just.
Okay, so okay. Listen up for break and turn back, inshallah.
Okay, sir. Thank you.
السلام عليكم. السلام عليكم.
وعليكم السلام يا دكتور.
حسابات حسابات دسمة شوي. كتيرة يعني، عاوز اقول مش دسمة يعني تقيلة، كتيرة وتشعبت وتنوعت مرة كده ومرة كده، فنرجو المذاكرة يا اخوان يعني ان شاء الله، يعني اعتبارا ده ان شاء الله من نهاية الكورس بكرة ان شاء الله. ارجو بقى باذن واحد احد ان نبدا المراجعة والمذاكرة عشان نثبت المعلومة. يعني زي ما انتم شايفين حسابات بسيطة لكن كتيرة كتيرة، مرة هنا ومرة هنا ومرة هنا ومرة هنا. ف يعني نعمل ان شاء الله كده المراجعة، والتوفيق ان شاء الله للجميع يا رب. بسم الله الرحمن الرحيم. شوف بسم الله الرحمن الرحيم. Now we need to start with the regulation. I will bring بسم الله الرحمن الرحيم. فين؟ Okay. Yesterday we spoke about the if we take started from the beginning, start with the basic obligation. What does it mean? You must do anything according to the regulations and according to the instructions for regulatory body, and you must take the license to do this or permission to do this, whatever the activities you did. And we continue with the basic framework. We have three principles of radiation protection and safety. These principles are justification, benefits greater than hazard for present and next generation, and also optimization, which is ALARA, reduce the exposure, the time, the possibility to accident to levels which is as low as reasonable achievable. Then limits, you must apply limit. For optimization, we can take into account the economical situation, and if it is sufficient, okay, we can do it. Otherwise, no. But we must apply the limitation, whatever the cost, limitation must be applied. Then we go to the meaning of safety culture and defense in depth, and later we spoke about the person who can work 18 years as radiation worker, can 16 years exposed to occupational dose, but with lower limit than normal, which is 20. Now 6. This is for students and trainees. And we said that anyone below 16 public, below 16 public, and we went to the classification of areas, control area, and supervised area, these two areas. Controlled area by definition, it is the area that a person can reach to 3/10 from the occupational annual limit, 6 millisievert per year, But if we used our 3 microsiever per hour for normal working conditions, can be increased, okay, depend on the situation. Like in Aramco, for example, saying 7.5 for the radiographers, because the time per day, 5 days a week, making occupancy factor about 2 hours per day. So now the main definition is 3/10 of the annual must not exceed than 6 millisievert. But we can to arrange to make something management, the detector give you in per hour, so we can say 3 microsieverts per hour, normal. Okay, supervised is area 1/10 up to 3/10. Up to 3/10. Really, if you need to design shielding, to make a design for shielding, here in Saudi Arabia here, of course you must apply the limit, of course. But if now you are a company and you need to take a license and you have a stored area, you must prove for them that outside the shield it is 0.375 microsievert per hour. 0.375 microsievert per hour. Say 0.375 microsievert per hour. This is not a regulation. This is take care when the accept must be like this. Okay. Now for controlled area now. No any person can enter controlled area. Only radiation workers. Only radiation workers. RSO, the technicians who has training, awareness training course. Public, no. Public, no. Whatever the public cannot enter the controlled area. Supervised area, yes, can. But under supervision of RSO. Under supervision of RSO. Of excellence, radiation excellence in the company. And in controlled area, not allowed to drink, to eat, to smoke. Not allowed to drink, to eat, to smoke. Because maybe there are some contamination, because you are now near the source, maybe contaminates, the source is contaminated, but you don't know. So now there is possibility to get internal contamination. So now, this is also alarm. Prevent eating, drinking, smoking, to reduce the possibility like hope to get doses, internal now. So smoke, eat, drink in this area does not allow. I found some people ask me, okay, we drink water, we take water for us, especially in summer season, to drink during the work. Okay. And this water, sometimes saying, okay, we got this water in the area and the radiation, and this water now is contaminated? No, at all. It is not contaminated. But put your luggage or something like this outside the controlled area. Outside the controlled area. So put everything outside controlled area. If you need to drink, okay, go there. Okay, eat and drink. But in controlled area, to avoid in case there are contamination, something like this. So controlled area, restricted area, only for radiation safety officer or radiation workers. Who is responsible inside the facility? Any administration procedure, this is a manager. Manager is responsible for any administration procedure. For execution, RSO. For example, who is responsible to or who is responsible generally for making the emergency plan? Manager. Who is responsible for execute this RSO? When you submit your file to KCare, you submit Rajesh, you submit emergency plan, you submit a lot of it. Who will sign for the letter to submit this? Who will sign? The person who will sign is manager. So he submit this. Who now responsible to execute this RSO? Okay, now in case of emergency, who is responsible to notify the KCare? Manager. Notify manager. And who is responsible to execute RSO? Okay, in exam, for example, if we ask it, in case of accident, what will be the first action to do? I will tell you the actions in the priority. First priority, to save, to rescue the injured persons. This is the first thing. To save, to rescue them. Second, if you are an aviation worker, notify after now, make a rescue for the injured person. If you are an aviation worker, second, you need, the first thing is, after rescue, is notify RSO. Inform RSO. If you are RSO, notify the manager. If you are the manager, notify KCare. So now, in exam, give you this option. First, notify RSO. Notify manager, notify KCare, saving life or rescue the injured person. First, if identify this option, contact RSO, contact Civil Defense Department, contact KCare, contact the police. No, contact RSO. So now, this is the first thing in case of accident. Now for a very important also frequently came an exam. In case of you need to make maintenance for the device. You have a projector maintenance. Now, excellent, well-qualified technicians can do this. First option. Second, high-quality engineer in this field. Third, manufacturer. Number four, anything. For making maintenance for the gauge, projector, here in Saudi Arabia is manufacturer who do this, not you, manufacturer. You will say the manufacturer is in QSA, global. This is the for the projector. Okay, whatever. The company is outside. in America, in Europe, whatever. I will tell you, okay. Now, QSA, for example, this global company for projector, has a agent here or distributor. And this distributor take license for them to distribute or to sell the product, the gauge. Like Endres Hauser, for example, here. Endres Hauser, we have Endres Hauser Arabiya here. It's a branch from Endres Hauser. This is big company for nuclear gauges. We have here. Now, this company will make the maintenance. And may this company make a training center here, and give you a training. And you have a license from them that you are certified to make this maintenance. Now you have certificate from the manufacturer that you have training and you are qualified to do this. So now you can make maintenance because you have a permission from the manufacturer to do this. As a result, you get qualified or suitable training to do this task. So now we can say manufacturer give you the license, give you the permission to do this. So yes, you can do now if you have this license. So finally you can say the manufacturer through you after getting license or directly from the manufacturer. For example, to make a maintenance for the projector, you have in your company one can make maintenance. You need to make maintenance each year. Each year, disassemble the projector and clean it and load, unload, store, something like this. So now, in your company, everyone can do this, but he take license and permission, take a training. In, for example, Abdul Latif Fuad, this is a distributor now here for QSA Global. Now, he take a license from the distributor. Now you do this under permission of the manufacturer. Yes, you can do this. But in case, in general, in the question came, manufacturer do this maintenance. You say, changing battery, I need to go to the manufacturer. No, of course, this is not a maintenance. This is not a maintenance. To change the battery of the device, something like this, this is not a maintenance. To change the guide tube, the crank, this is not a maintenance. I mean maintenance. Maintenance meaning maintenance. You deal with the source. You disassemble something. And after this, you make assembly, install. This is manufacture. Here in Saudi Arabia, you must say manufacturer. Now, for example, also, if you have a source, and you need now, you don't need this source now, this nuclear gauge now. You must return back to the manufacturer also. So you need to return back to the manufacturer. Need re-export it again. You need to re-export it again. So cannot keep here. Cannot keep here. You must return back to the manufacturer or re-export it again for that manufacturer. Okay. The license here, number 2.2. The license, who is engaged in activities involving normal or potential exposure shall appoint radiation protection officer for carrying out the technical actions. For technical action, radiation protection officer, and the tasks carrying out the technical action and tasking related to the responsibility. So this is the responsibility for technical action, RBO. For administration action, manager. Who is responsible for applying for applying the radiation protection for radiation protection program. Manager for general obligation or basic obligation. Manager. Technical issues are radiation protection officer, but any other thing is manager. Who is responsible, for example, who is responsible for using the gauge in suitable way, in safe way, in safe manner? Worker. Now, in regulation here in Saudi Arabia saying, for example, nuclear gauges, portable nuclear gauges, one person as RSO for 20 nuclear gauging, portable. If it is fixed, one radiation protection officer for 40 nuclear gauges. So one person, one RSO supervised for 20 nuclear gauges. For radiography, one RSO for five projectors. Now, who is responsible for using the device, the nuclear gauge, in safe way? Worker. I supervised for him only, but to do the worker, this is his responsibility. After he getting the suitable training, and you provide for him all tools. Now, this is the responsibility of him. If, for example, I take a source and go to the site, taking everything, radiation protection training course I take, calibrated survey meter I take, TLD I take, everything I have, and now I lost this source. Who is responsible? Worker is responsible for this. Because this is his responsibility to execute this. After getting that enough, or getting all the requirements for safety. Of course, we need to read this in detail, but I give you the most important thing, the one that came in exam. For example, this is a specific responsibility of radiation protection officer. Please, you can read it. Okay.
So one question, sir.
Yes.
Who is responsible for the safety of worker? Is it manager, it is RSO, or is it worker himself?
Okay, safety of workers. Okay, now, for technical issues, radiation protection officer. For example, providing TLD, to give TLD for him. This is the radiation protection officer. To give and take and read TLD, RSO. But to providing, to bring TLD, to buy TLD, to make contract with the third party, this is a manager. Manager must provide the resources, financial resources for this. Assume now RSO asking for the manager, but manager say, okay, no. Responsibility of him. To sign a contract, who will sign the contract? Manager. But now, manager do the work. He make the administration issue PO, and now, who now responsible to provide this TLD and take and send for the calibration lab and receive the report? This is RSO. So now let's read this. This is a general form. This is some responsibility to be a preparation of all this word, technical aspect. TLD, just administration, provide TLD in the facility. Now I have TLD. Who will take this TLD? Our radiation protection officer. Take this. Now distribute. This is now start his responsibility now. But he don't have TLD and asking. This is the responsibility of the manager. So any technical aspects and procedure for the aviation protection program, okay, including emergency plan and the quality assurance program, technical aspects, supervision of the aviation protection officer. Technical aspects. Always see if it's technical or not. This is RBO. Administration. This is the manager. Workers. Also, to do the work according to safe procedure, this is a worker. This is a worker. Okay, for the now, okay, we have here very important thing. Potential exposure. Okay. Potential exposure. We have normal exposure. Normal like our exposure, chronic exposure. We have chronic exposure. Chronic exposure. What is the meaning of chronic exposure? Huh? Small amount of doses for long time, like us as a worker. Like the radiation background, this is chronic dose. Acute dose, big amount in a small time. This is acute dose. This is type of exposure. We have occupational exposure for workers and trainees and students. This, and we have, as you say, medical exposure. This is out of scope. This is medical out. General or public exposure, chronic exposure, acute exposure. We have another term here, which is potential. Potential. What is the meaning of potential? This is exposure. It is a possibility to do this. This is when you design a facility, nuclear facility, you take into account scenarios of accident. We call this now, we assume that exposure happened due to some fault or mistakes from the operation, and let's assume exposure for the worker. This is called potential exposure. So this is during design stage, we assume some accident to design the facility to stand, to resist this situation, and we say we will be safe in case even of accident. So this is potential exposure. It defined as exposure that is not expected to be delivered with certainty, probability. Let's imagine a scenario to maybe happen, and may, in case of it happen, the person will expose to this amount, but may result from an accident at a source or owing to an event or sequences of event of a probabilistic nature. Maybe happen. For example, why Chernobyl was a severe accident? Chernobyl. Why Chernobyl is a severe accident? Why? Because this reactor, they must, from potential exposure point of view, they must put in confinement. There is a building, big building. All this reactor must be inside this building. They didn't make confinement. So if they took into account maybe explosion for this reactor, so now this containment, a huge building, all the reactor do this, but in Russia at this time, Soviet Union, they don't pay a lot about safety. So they didn't make this confinement, this containment to put this reactor inside. So in case of they have containment, all this that released to atmosphere will be inside this containment. So they don't take into account the potential exposure. Potential exposure is expected dose that they received in case of accident. This is the meaning of potential exposure. For example, driver. Travel with radioactive source. There are some possibility to get accident. Sphere accident. Now, the vehicle turning more times, 3, 4 times, 4 times. I take this into account and design a box with a shielding and strong enough to stand with, to resist this thing. And I say, in case of something happen, the maximum amount of activity, can I carry this amount? And may, in case of accident, a person receives this amount. So now it's in design stage only. Now, one important also question in exam, when you design or try to protect people from waste, nuclear waste. So we have a nuclear waste, assume. Now you need to design, to take into account radiation protection and safety when you design or construct the waste facility. You must take into account which type of exposure, potential, public, chronic, acute. You must take for waste design facility, you must take into account the public exposure. You must design your facility taking into account the public exposure. Why? Because this facility will stay in the and work and use it for many years. This will be a site to handle waste and will keep as a to handle waste forever. So we must take into account that public will not receive greater than the limit of public. So design this for public exposure. The limit for public exposure. This came usually in exam. I found this many times in exam. For waste management, radiation protection and safety concept take into account public exposure. Public exposure. Not occupational, public. Take into account this. Understand this. Okay. Now, we saw yesterday. In emergency, you will say, okay, there is no limitation, especially in case of you life saving. You can reach up to 5 recommendation. This is only recommendation. And this is a structure of radiation protection program. We said yesterday, committed administration, selection and training, surveillance of occupational exposure, public also surveillance for public exposure. Now make everything as a quality assurance program, then emergency plan. This is what we said yesterday about these items. Let's go deep and this is here, classifications of working area. This, as we said, controlled and this is some regulation, local rules. So you can read it also, as we said, we explained this is during the speech. And also now in controlled area, TLD, no one can enter this area, even to the radiation worker, without TLD. Must TLD. Now TLD for radiography practice must read each month regulation each month. So now you need to each month return your TLD and bring new one, take new one. Each month. So you have 12 reading per year. And the total reading must not exceed than 20 as per regulation. For nuclear gauges, each 3 months. Each 3 months. Nuclear gauges, each 3 months. So 4 reading only in 1 year. For nuclear gauges, for well logging, for transportation, any practice other than radiography. Radiography each month. Other practices each 3 months. You return back TLB and take one new. Now, for calibration, for radiography 6 months. 6 months. Wipe test each 6 months. You need to make wipe test. Wipe test, calibration of the detector each 6 months. Each 6 months. This is regulation. Before it was 1 year. It was 1 year. Each 1 year make calibration. And wipe test also 1 year. Now it become 6 months. 6 months for radiography, calibration, and wipe test. 6 months. For now, wipe test and calibration for other practices, by regulation 1 year. Each 1 year. But KCARE say it is recommended to be 6 months. Recommendation only. Recommendation, not obligation. Recommendation, each 6 months. But regulation, each 1 year, make wipe test and wipe test and calibration. Each 1 year for any practice other than radiography. For radiography, 2 workers, 2 technicians for one nuclear, for one radiograph, for one camera, for 2 technicians for each projector. For nuclear gauges, 1 technician for 1 projector, for 1 nuclear gauges only. 2 detectors for each projector. 2 detectors, survey meter for each projector. For nuclear gauges, 1 survey meter for each nuclear gauge. This is for gamma sources, for nuclear gauge. For neutron sources, 1 detector for neutron. 1 detector. Only 1 detector for neutron for each 5 neutron source. For 5 neutron source, you can buy only 1 detector. If you have 6 neutron source, you need to get 2 detectors. If you have 4 neutron source, only 1 detector is enough for neutron. For gamma source, 1 source, 1 detector. 1 source, 1 detector. For radiography, 2 radiation source, 2 radiation detector, 1 source, for 1 projector. We speak about record and detail and okay. Now let's go to the radiation contamination. Okay. Tomorrow, inshallah, we'll speak about this type of detector, which is called liquid scintillation detector. So I will, tomorrow, inshallah, I will mention this point. Okay? When we study that detector. Now for the West now. For the West. Okay. For the West. Now, for any unused radioactive source, you must return back to the manufacturer. You must return back to manufacturer. Okay. Now, for the sources, for the liquid sources, long-lived. What is the meaning of long-lived radioactive sources? Long-lived meaning half-life greater than 1 month. 1 month. Half-life greater than 1 month. 30 days. 30 days. If the half-life of a radiation source greater than 30 days, this is called long-lived radioactive source. If it is less than 30 days, this is called short-lived radioactive source. Now, we need to read this, number B. Say number A here. As you see, all sealed sources, and we work with sealed sources. We work with sealed sources. All sealed sources and other solid sources must return back to the producer. Back to the producer, country of origin. Country of origin or producer must return back to country of origin or producer, manufacturer. Now, for short-lived waste, meaning half-life is less than 1 month, 30 days. Now, this is different from norm. Norm is long-lived. Radium has half-life greater than 1,600 years. Greater than 1,000 years. So now we speak about now, short-lived now. Long-lived you will see now. So now, short-lived, what we can do for this? You can store. But safely stored. Until its activity decrease to a certain value. Take care, say, if short-lived radioactive waste. Now, keep it in your site. Make it decay. Leave it for 1 year. So it will decay so much, until a certain value. This value determined from take care. Saying now, if you reach to this value, you can now release this waste to normal waste. For example, now in hospital, they give iodine 131 for the patient. In capsule, he takes this in capsule and drink water. Now, he has iodine 131. The half-life is 8 days. This patient went to bathroom, for example, and used, for example, some tissue, some contaminated now. They take this urea, for example, from bathroom and put in containers. Leave this container for about 3 months, 4 months. Now, the value of activity become very low background. So now they can release to the, as you see here, release to normal waste. Now they can release in the normal waste. As you see, this is the, released with normal waste. Short-lived. Now for long-lived, like carbon, liquid sources, because carbon usually coming in liquid. So with respect to long-lived liquid sources, carbon, and this carbon is soluble in water, can dissolve in water. Now, you can make dilution, put water, and dilute it. Then you can release certain quantity every day, not all quantity, certain quantity every day in sanitary system. This is a sanitary system you can release in it. So if it is carbon 14, why we give this carbon 14? Because this is a soluble, any long-lived but soluble in water, can released in sanitary system. But take care, you must take permission from take care to do this. You must take permission, license from take care to do this. You cannot do by yourself. You must take permission, license to do this. Okay. Now, C. No, this is now, let's go to the E. Now, for solid low level waste, we speak now about waste, not source. Waste. Solid low level waste, which contain long-lived radionuclides. Long-lived radionuclides, like what? Like norm. Like norm. Now, it may be disposed of by containing in shallow repositories. But to do this, again, you need to take a permission for take care. Remember the basic obligation, don't do anything with radioactive source without permission. You must follow the regulations. One of the regulation is take a license. Okay, what I can do? Only keep. Don't make a hole and now dispose, because you need to take a license for this site. For this site, you need to take a license. You need to make some study for the groundwater. Maybe this is there's some groundwater, and you will contaminate it. You need to build, for example, insulated layers. You need to do many things. You need to do monitoring to measure the external dose, because public, you need to do everything. But this is after getting the permission from KK. This is why I told one of our friend, Norm, there is no company here taking license to deal with it. Only keep in your site safely. If you need to handle it, now you need to notify KK, taking license, then you can make treatment now. One of the treatment is to make a hole, dig, and put in the repositories. Stored area. Okay, this is, yes.
هذه البول انجكشن اللي يسموها ديبول انجكشن دواء treatment of normal.
Yes, sometimes Aramco does this. You are working Aramco?
Yes.
Yes, this is sometimes Aramco do this. Return back this norm in the ground.
But still not doable now, not practical so far. No.
I deal with the EBD there, and we treatment something like this, but after getting all the required permission.
Okay.
All requirements about this. You know, Aramco follow certain standards. We cannot, okay, this standard is very restricted about this with the EBD session there. Okay, now, with respect to solid, solid, high level, not low level, solid, not norm now. Situation now is, it may be disposed by concentrating you can reduce the volume, make compressed, making, and this mix to cementize it. You can deal with chemical treatment to reduce the size, a lot of things. But this is not allowed here, but only this regulation. In case of company take a license. And this is the thing. And then after you make solidification, reduce, and you can now containing this barrels in deep repositories for final disposal. But again, you need to take a license for the site and a lot of things. You must go to KKR first. This is how to deal with waste. Please take care, because this one. Short lift. What you can do, keep until decay and go to the send for normal. And also for this with respect to solid low waste, like norm. It may dispose by containing in shallow, not deep, shallow. Okay. This is how to deal with waste. Now it's the information in the record shall be done by Radiation Protection Officer responsible for the record, for the registration of the record, RBO. Because it's technical work now. Okay, I received the report from King Fahd University, TLD. I received, Radiation Protection Officer received. Now, keep this is his responsibility. Send a copy for KKR, must send a copy for KKR. This is his responsibility. Okay. Now we finished now from the, yes?
جامعة الملك فهد فيها
Yes. Yes, there is a lab there for dosimetry lab to measure the TLD.
How can you break the norm transmit, the norm detector, for example?
No. For norm, I will be frank with you. They will accept this norm detector to make calibration, like also here. But this is not correct calibration. Norm detector, you need to return back to the manufacturer to make calibration. They have their equipments that contain norm as a source in what is called equilibrium state. This is very important condition called in equilibrium, in secular equilibrium state. Now you will face this situation in real secular equilibrium state of isotopes of norm. This is issue must be satisfied, then you can calibrate. Otherwise, you have a calibration. Remember when I told you the interaction of radiation, especially gamma and Newton, depends on the energy. Remember when I told you half value layer, for example, depend on the type of source, cobalt, cesium. Remember when I told you the photoelectric effect depends on the 1/E of to the power 3, and in the intermediate region, competent, and in the low energy is photoelectric mainly. Now you need to make the response of your detector for norm for these energies, for the radium, for uranium, for lead 210, for bismuth, with a lot of isotopes, for bismuth 214. So you need to get calibration factor regarding to this, because the performance or sensitivity or the function of the detector and the reading depend on the energy. So if you put cesium, this is different completely from the energy of the norm. If you put cobalt, another, the worst case. So now you need to return this back to manufacturer. This is the correct way. I found in some cases, I need calibration because I can't enter, for example, to the site without this label, calibration. Go to the calibration lab here and take the license. Stick the label, calibrated. This is not calibration. This is not calibration. For norm, I say for norm. For other detectors, yes, you can calibrate in King Fahd, in King Abdulaziz, King Fahd University, King Abdulaziz City for Science and Technology, CAST, and even for King Faisal Hospital, research center there. They have a calibration lab, calibration lab. Also, another mistake also happened regarding this topic. No any lab here can measure the dose from neutron sources. The persons who work with nuclear gauges, for example, have cesium for Truxa, for example, 10 millicurie cesium and 40 millicurie americium beryllium. Now, they have TLD. This TLD is 2 ships, only measure for gamma, deep and shallow dose. Where is the neutron? No. There is no neutron source here to calibrate this. So if you send your calibration, your detector for neutron to send for calibration, really, there is no calibration. They brought in, you can say, traceability, estimation. But this is another thing. So if you need really to make calibration for your neutron detector, send for the manufacturer. For norm, also send for the manufacturer. So now we finished from the inshallah, but you need to read it, huh? You need to read it. Take only, this is the most important and the regulation that you apply in the field. Tomorrow, inshallah, we'll speak about detectors and measurements. Detectors and radiation measurements, radiation detection and measurements. Okay. See, inshallah, you tomorrow. Inshallah, meet you, inshallah, and you are well. تقابل إن شاء الله على خير يا رب. وأي سؤال أي استفسار؟
الله يعطيك العافية، معليش تعبناك اليوم معنا، واضح اليوم انك تعبت معنا كثير صراحة.
لا تحت أمرك يا أخوي.
بارك الله فيك.
الله تحت أمرك، ده واجب إن أنا لازم أعمله، واجب يا أخي الكريم.
الله يجزاك خير. بارك الله فيك.
ماشي يا أخي الكريم.
يعطيك العافية يا مهندس أشرف، شكرا.
الله يبارك فيك، الله يبارك فيك يا الكريم، الله يعطيك الصحة.
الله يعطيك العافية دكتور.
شكرا يا أخي الكريم، الله يبارك فيك. نتقابل إن شاء الله على خير غدا إن شاء الله. meet you إن شاء الله tomorrow إن شاء الله. نقول لكم السلام عليكم.
See you tomorrow.
وعليكم السلام.
مع السلامة. مع السلامة. Goodbye, my friends.
Yeah, hello, Mr. Ashok. I have one question.
Yes,
No.
okay. Yes.
With this RSO certificate, whether we can work in nuclear gas? Right.
Please make your voice lower voice because it's so close. I hear something like this.
Okay. With this RSO certificate, whether we can work in nuclear gas, right?
RSO certificated in nuclear gauges?
Yeah.
Yes.
We can work or not?
Is what?
We can work or not in nuclear gas site.
In nuclear gas site, you can work in nuclear gas site if you have radiation protection officer license for this.
Yes.
Could you please write? I can't tell you. Could you please write it in the chat, please?
Sure.
Okay, please. Okay. One more question. If a source went missing or stolen, what action should RSO take first? The first action in case if a source went missing or stolen, first action, RSO must notify the manager directly. Don't contact police, don't contact civil defense, don't contact KK. As RSO, notify the manager directly. Manager will notify the KK and police. Then who is responsible to notify KK, police? The manager. As I told you, connection about any action or anything between the facility and or the company and the KK, who is signed there? Manager responsible. Manager sign. So RSO notify manager. Then manager notify the KK and police. With RSO certificate, shall we can work inside which having a nuclear gauge? As I understood, you are RSO, you have certificate, and you went to a site to do something, and you find another company working with nuclear gauge. Can I stay in this area? Yes. And if you are the RSO for this company who use nuclear gauges, yes, you can. You can. You are. If you are in the company, and your company use nuclear gauge, and you are RSO in this company, of course, you have the certificate that you are qualified and well trained to handle situation like this, to work in this site. If assume you are RSO and you went to site and you find that they have some work there and use nuclear gauges. Okay, can I stay in this site? And yes, you can, because you have qualified and you have TLD, of course, for you. Okay, now, okay, you can. Why not? You are a qualified person. You take a license.
Okay, thank you.
I understood the question in the right way, or it's another thing.
The same.
You are a qualified person to deal with additional sources. You have a license. Like what? I will give you an example. Like what? You have, for example, a license first class of to drive a truck. This is the first class or something like this. Because it's for private, for the bus, another for the truck is the highest level. Now you have something like this. Now you can drive any truck. You can drive any truck. Even you can drive this private vehicle. You can drive bus. So you are qualified as RSO. This is the highest level now. You can handle the situation in any place contain radioactive sources. Okay. Assume now I went to my colleague working in another company. I'm RSO. I went to my colleague working in another company as RSO also. He is RSO, and I found him working inside. I can go to him inside in controlled area. I have TLD because I am a radiation worker. If there is need to be with him, for example, there is a need. ALARA principle. Remember, ALARA principle. To help him for a certain situation, emergency situation. Yes, I can. Because I'm qualified person. Okay. I hope it's clear. I hope. I understand well.
Okay, thank you.
Okay. Okay, see you later inshallah. Tomorrow, bismillah.